What if everything you think you know about reality is only a tiny sliver of a much grander, far stranger picture? We live our lives assuming the universe is a single, solid thing, a fixed stage upon which the drama of existence unfolds. But what if that stage is constantly splitting, branching, multiplying into countless parallel versions of itself, each one as real as the one you're experiencing right now? This is not science fiction. This is the astonishing frontier of modern physics, a realm where the rules of common sense break down and the very fabric of reality becomes fluid, uncertain, and breathtakingly multidimensional. Welcome to a journey through the quantum landscape, where particles exist in multiple places at once, where observation shapes outcome, and where the universe may not be a lonely island of existence, but one of infinite islands in an endless sea of possibilities. For centuries, we've looked up at the night sky and wondered about our place in the cosmos, but today that question has taken on a whole new dimension, literally. We're beginning to understand that reality might be far more vast, more layered, and more mysterious than we ever dared to imagine. In this video, we're going to explore 30 of the most profound and provocative theories about the quantum nature of our universe. From the many worlds interpretation to holographic principles, from simulated realities to cosmic consciousness, we'll venture into ideas that challenge not only how we see the cosmos, but how we see ourselves. This isn't just a list of abstract concepts. It's an invitation to expand your mind, to question everything, and to glimpse what may be the greatest story ever told, the story of all possible realities. So settle in, open your curiosity, and let's begin. Our journey into the quantum unknown begins not with a distant star or a black hole, but with a simple yet utterly baffling experiment. Picture a single electron fired at a barrier with two slits. Common sense tells us it should go through one or the other, but in the quantum world, that electron does something miraculous. It behaves as if it passes through both slits at once, creating an interference pattern with itself on the other side. It exists in a state of pure potential, a superposition of all possible paths until the moment we look. The act of observation, of measurement, seems to force it to choose a single, definite reality. This is the famous double-slit experiment, and it presents us with a profound mystery. What really happens during that moment of collapse? Where do all those other possibilities go? In the 1950s, a brilliant young physicist named Hugh Everett offered a solution so radical, so audacious, that it was largely dismissed for decades. He proposed that there is no collapse, the possibilities don't vanish. Instead, he suggested that every single quantum event, every flicker of potential, every possible outcome actually happens. When that electron is measured, the universe doesn't choose a path. It takes both paths. The very fabric of reality splits, branching into two separate, equally real worlds. In one world, the observer sees the electron go through the left slit. In the other, an identical version of that same observer sees it go through the right. Both realities are now forever separate, unfolding independently within a vast and ever-expanding multiverse. This is the many worlds interpretation. It removes the need for a mysterious observer effect and paints a picture of a profoundly democratic cosmos where every possibility is realized. It means that for every choice you've ever made, a new universe was born where a different version of you made the other choice. There is a reality where you said yes to that job offer and another where you said no. A universe where that lucky break went your way and another where it didn't. While you're sitting here watching this video, another version of you is a celebrated rock star, another is an astronaut gazing at Earth from orbit, and another, in a timeline where evolution took a different path, might not even be human. These aren't mere fantasies. In Everett's view, they are all physically real parallel worlds, forever separated from our own by the branching waves of quantum probability. The implications are both exhilarating and deeply humbling. It suggests a cosmos of literally infinite variety, where every tragedy is averted somewhere, every dream is realized, and every story that could possibly be told is being lived out in a universe of its own. It transforms our universe from a single, lonely narrative into an endlessly sprawling library of all possible existences. Yet, we are forever confined to a single branch, aware only of the timeline we inhabit, forever wondering about the roads not taken. This isn't just a theory about particles, it's a theory about us, about the nature of existence itself, and our place within an infinite tapestry of realities. But if every possible outcome occurs in its own separate reality, where does that leave you, the individual stream of consciousness experiencing this very moment? This line of thinking leads us directly to one of the most personal and philosophically jarring implications of the many worlds interpretation, a thought experiment known as quantum immortality. The premise is as simple as it is chilling. Imagine a modified version of the classic Schrödinger's cat scenario, but this time you are in the box. A diabolical quantum device is set up at a random moment triggered by the decay of a single atom. It will either fire a lethal bullet or simply click harmlessly. From an outside perspective, there are now two versions of events. One universe where you are tragically killed, and another where you survive, hearing nothing but a quiet, harmless click. The theory of quantum immortality posits that your conscious experience will only ever follow the branches of reality in which it continues. You cannot experience being dead because consciousness ceases at that point. Therefore, no matter how low the odds of survival might be, 1 in a million, 1 in a billion, your subjective experience will always find itself in the timeline where you miraculously live. From your first-person point of view, you would become seemingly invincible. You could step in front of a speeding train and, against all probability, find yourself standing unscathed on the other side, having somehow slipped into the universe where the train was delayed by a single second or your foot caught on a track tie just right. The universe where you died would be just as real, but there would be no you there to experience it. This isn't a prescription for reckless behavior, of course. It's a profound logical consequence of taking the multiverse seriously. It forces us to confront deep questions about the nature of identity. Are you the same continuous consciousness, or are you merely a momentary pattern that flickers into existence along a specific, survivable branch? Each near miss might not be a brush with death, but a branching into a new world where you persist, while another version of you meets an end. The you reading this sentence is the product of an unimaginably long chain of such quantum survivals, a consciousness that has, by definition, never experienced its own cessation. This idea stretches the concept of self to its breaking point, suggesting that what we consider our singular life might be a fragile thread weaving through an infinite tapestry of possibilities, forever avoiding the snip of the scissors. But if the many worlds interpretation offers a sprawling, infinite canvas of reality, then its great rival, the Copenhagen interpretation, paints a far more intimate and mysterious portrait. Developed in the 1920s by pioneers like Niels Bohr and Werner Heisenberg, this view doesn't just challenge our idea of the universe, it challenges our role within it. At its heart is a concept so counterintuitive it seems almost magical. The universe remains in a fuzzy, undefined state of pure potential until we, the observers, force it to make a decision. This isn't about branching realities, it's about a single reality that doesn't even fully exist until it is seen. Think of it like this: before you open your refrigerator, you might assume its contents are fixed. A carton of milk is either inside or it isn't. But in the quantum world governed by the Copenhagen view, that carton of milk exists in a bizarre superposition. It is both in the fridge and not in the fridge, a blur of probabilities until the moment you open the door and look inside. Your act of observation is what collapses this wave of possibilities into a single, solid fact. You didn't just discover whether the milk was there, your looking literally made it be there. This is the famous wave function collapse, and it places human consciousness, or at least the act of measurement, at the very center of the cosmic machinery. Why would brilliant physicists propose something that sounds so philosophical, even mystical? It was born from the need to make sense of the baffling results of experiments like the double slit. They weren't just guessing, they were constructing a mathematical framework that could accurately predict the outcomes we see in the lab. The equations worked beautifully, but they came with this strange, unavoidable implication: measurement creates reality. Werner Heisenberg's uncertainty principle is a cornerstone of this view, stating that we cannot know certain pairs of properties, like a particle's position and its momentum, with absolute precision at the same time. This isn't a limitation of our tools, it's a fundamental property of nature itself. The particle doesn't have a definite position until we measure it. This interpretation has profound consequences. It suggests that at its most fundamental level, the universe is not made of solid, independent objects, but of possibilities and probabilities. The world we perceive as concrete and stable is in fact a shimmering mirage that solidifies only when interacted with. It creates a stark division between the quantum realm, where these strange rules apply, and the classical world of our everyday experience. Critics often point to this as a weakness, asking where exactly the line is drawn. Does a cat count as an observer? What about a camera? The Copenhagen interpretation is famously silent on the mechanics of the collapse itself. It simply states that it happens, and the mathematics that describes it is incredibly successful. Ultimately, the Copenhagen view presents a universe that is deeply participatory. We are not passive inhabitants of a preordained world. Through the very act of questioning, of experimenting, of looking, we are collaborators in creation, constantly bringing the universe into sharp focus from a haze of potential. It is a humbling and empowering idea that the solid ground beneath our feet and the stars in the sky above gain their definitive form, in some small way, because we are here to witness them. So if the Copenhagen interpretation places us at the center of a mysterious collapse, and many worlds suggests we are forever branching into new realities, is there a way to resolve the measurement problem that doesn't require such dramatic philosophical leaps? This is where our fourth theory enters the stage, offering a powerful and increasingly favored solution. It's called quantum decoherence, and it doesn't so much answer the question of what reality is as it explains why reality appears to us the way it does. It provides the crucial missing link, the mechanism that transforms the blurry quantum world into the sharp, definite universe we perceive every day. To understand decoherence, we need to revisit our friend, the electron in superposition. We say it's in two places at once, but that's only true if it's perfectly isolated from the rest of the universe, a near impossible feat. In reality, that electron is constantly bombarded by its environment. A stray photon of light bounces off it, a passing air molecule gives it a nudge. Even the faint whisper of a gravitational field tugs at it. Each of these tiny, insignificant interactions carries away a tiny piece of information about the electron state. This is the heart of decoherence, the relentless, uncontrollable exchange of information between a quantum system and its environment. Imagine you're trying to have a serious, private conversation in the middle of a roaring, crowded party. You can't maintain a single, coherent thread of discussion because every few seconds someone bumps into you, a snippet of another conversation intrudes, or the music drowns out your words. Your private chat quickly becomes entangled with the noise of the entire room. It's not that your conversation ceased to exist, it's that it became irreversibly mixed with everything else, losing its distinct individual character. This is precisely what happens to a quantum particle. Its delicate state of superposition, its ability to interfere with itself, is exquisitely fragile. The constant interaction with the environment is like that noisy party. and it rapidly destroys that coherence. The brilliance of this theory is that it doesn't require wave function collapse or splitting universes to explain why we only ever see definite outcomes. The superposition is still there mathematically. The electron is, in a sense, still in multiple states, but the phase relationship between those states, the thing that allows them to interact and create interference patterns, has been scrambled and lost to the environment. The different possibilities can no longer see each other. From our perspective, the system has effectively chosen a single classical state. It appears to have collapsed not because of a conscious observer, but because it can no longer maintain its quantum connection to its other potential selves. The environment acts as a continuous, involuntary measurement device. This process is not just theoretical, it's been demonstrated repeatedly in laboratories around the world. Scientists can now watch decoherence happen in real time, observing as beautiful, coherent quantum states gradually dissolve into classical definiteness as they interact with their surroundings. This is why we don't see quantum weirdness in our daily lives. A baseball never exists in a superposition of being simultaneously hit and not hit because it is constantly colliding with trillions of air molecules, each interaction relentlessly measuring it, forcing it to pick a state. Decoherence provides the bridge, showing how the definite world we know emerges naturally from the fuzzy quantum substrate simply through the unavoidable process of interaction. However, it's critical to note what decoherence does not do. It doesn't tell us which outcome becomes our reality. In the language of the equations, it explains why the interference terms vanish, leaving us with what looks like a set of probabilities. But it doesn't select one single, actualized outcome from the menu of possibilities. For that, some physicists believe decoherence must be combined with another interpretation. It seamlessly partners with the many worlds view, for instance, explaining why we become trapped on a single branch, unaware of the others. Our local environment becomes correlated with one specific outcome, and we, as part of that environment, are locked into that particular story. Decoherence doesn't solve the deepest metaphysical puzzles, but it solves the practical one, showing us the mechanism that hides the dizzying quantum truth from our classical perception. But if decoherence explains how the quantum world appears classical to us, it still leaves a deeper mystery untouched, the sheer strangeness of what is happening beneath the surface. For a perspective that is perhaps even more radical than branching universes or conscious collapse, we must turn to a theory that fundamentally rewrites our understanding of cause and effect. This is the transactional interpretation proposed by physicist John Cramer in the 1980s, and it suggests that the quantum world operates through a form of negotiation, a handshake across time itself. This interpretation starts with a simple but profound question. What if the wave function, that mathematical description of quantum possibilities, isn't just an abstraction, but represents a real wave traveling through space and time? And what if that wave doesn't just travel forward? Cramer's brilliant insight was to take the mathematics of quantum theory absolutely literally. The equations show that for every ordinary wave moving forward in time, there is also an advanced wave, a mirror image moving backward in time. Most interpretations treat this as a mathematical quirk to be ignored, but the transactional interpretation says both waves are equally real and physically significant. Here's how it might work in practice. Imagine a single atom excited and ready to emit a photon of light. According to this view, that atom doesn't just shoot the photon out randomly. Instead, it sends out what Cramer calls an offer wave in all directions, and this wave moves forward through time. This wave is a probe, a signal of potentiality, spreading out to explore all possible futures. It travels until it encounters a particle that can absorb it, like an atom in a detector screen or even in your eye. Now, something truly bizarre happens. That absorbing particle, upon receiving the offer wave, sends a response, a confirmation wave, backward in time, retracing the exact path of the offer wave to the original emitter. It's like sending out a proposal and getting a signed contract returned to you instantly, finalizing the deal. It is only when this handshake is complete, when the offer wave moving forward meets the confirmation wave echoing back from the future, that a photon is actually emitted and absorbed. The transaction is finalized. This two-way exchange in time is what creates what we perceive as a single, definite particle moving from one point to another. The photon's journey is not a billiard ball flying through space. It is an event solidified by an agreement between the past and the future. The most likely transactions, the ones with the strongest waves, correspond to the outcomes with the highest probability, beautifully explaining the statistical nature of quantum mechanics without any need for collapse. The implications for our understanding of time are staggering. This interpretation treats time with a beautiful symmetry. The past influences the future just as we always thought, but the future also influences the past. Our classical one-way arrow of time emerges from this deeper, two-way street of quantum communication. It provides an elegant explanation for the infamous double-slit experiment. The offer wave goes out through both slits, exploring all paths, and the confirmation wave returns from the detector, selecting the path that will be realized. The interference pattern is simply the result of which paths are reinforced by this handshake across time. While it remains a minority interpretation, the transactional interpretation forces us to confront the possibility that our linear experience of time may be a grand illusion, an emergent property of a universe where the fundamental conversations between particles transcend our everyday notion of before and after. It suggests that at the quantum level, the entire timeline of the universe is interconnected in a way that makes the distinction between past, present, and future far more fluid than we could have ever imagined. While the interpretations we've explored so far accept the inherent randomness or multiplicity of quantum events, a persistent group of physicists has asked a more fundamental question: what if the quantum world is not random or fuzzy at all? What if this appearance of chance is merely a veil, hiding a deeper, completely deterministic reality where particles have definite positions and follow strict causal laws, just like planets orbiting the sun? This is not a new idea. It was there at the very birth of quantum mechanics, championed by a brilliant French prince, Louis de Broglie, in the 1920s. His theory was ultimately overshadowed by the Copenhagen view, but it never truly died. It was resurrected decades later by an equally brilliant and determined physicist, David Bohm, and it offers a stunningly clear, almost classical picture of the quantum realm. This is pilot wave theory, also known as the de Broglie-Bohm theory, and it dares to suggest that the quantum world is far more understandable than we've been led to believe. The core of this idea is beautifully simple. It proposes that every particle, like an electron, is a real, point-like object with a perfectly well-defined position and trajectory at all times. It is never in two places at once, so what explains the bizarre behavior in the double-slit experiment? The particle is not alone. It is accompanied and guided by a mysterious, invisible force field, a pilot wave. This wave is a real physical entity spread out across space, and it interacts with the particle, telling it exactly where to go. Think of it like a tiny boat bobbing on a choppy ocean. The boat itself has a specific location, but its path is completely determined by the waves and currents beneath it. The pilot wave is that ocean, a hidden medium that guides the particle's motion. In the double-slit experiment, the electron particle goes through only one slit. That's definite, but its accompanying pilot wave, being a wave, goes through both slits. On the other side, the two parts of the pilot wave interfere with each other, creating a complex pattern of ripples and troughs. The particle, riding this wave, is then guided into the regions where the wave is strongest, the peaks of the interference pattern. It is steered away from the troughs. When you fire millions of electrons one by one, each guided by its own pilot wave, they naturally build up the famous stripy pattern on the detector screen. There's no mystery, no collapse, and no branching universes. The outcome is predetermined from the moment the particle is emitted. Its path is set by the shape of the pilot wave. The apparent randomness of where each particle lands simply comes from our ignorance of the wave's exact initial configuration. This theory is profoundly satisfying because it removes the need for observers and conscious collapse. Reality exists independently whether anyone is looking or not. Schrödinger's cat is either definitively alive or definitively dead before the box is opened. There is no spooky superposition. The mathematics of pilot wave theory is completely equivalent to standard quantum mechanics. It predicts all the same experimental results, but it offers a completely different story, a narrative of a real, objective world governed by cause and effect. For many, this is a welcome return to a universe that makes intuitive sense, a universe that Einstein would have approved of, fulfilling his belief that God does not play dice. Yet, this clarity comes at a significant cost. To work, the theory must be explicitly non-local. This means the pilot wave guiding a particle here can be instantly influenced by events happening on the other side of the universe. If you change the setup of the double-slit experiment after the particle has already passed through the first slit, the pilot wave changes instantaneously, altering the particle's path in a way that seems to violate the cosmic speed limit of light. For David Bohm, this non-locality wasn't a bug. It was a feature pointing towards a deeper, unbroken wholeness to the universe where everything is connected in a fundamental, immediate way. It suggests a cosmos that is less a collection of separate objects and more a single, seamless, interconnected entity, with the pilot wave acting as a kind of cosmic information field that ties it all together. This view challenges not only standard quantum theory, but also our deepest assumptions about space, time, and the nature of separation itself. While pilot wave theory restores a definite reality independent of us, another interpretation takes the observer's role to its ultimate, most personal conclusion. This view doesn't just place consciousness at the center of the quantum drama. It suggests that the entire mathematical framework of quantum mechanics is not a description of the external world, but a tool for navigating it, a personal guidebook for each individual agent. This is quantum Bayesianism or cubism, a radical reinterpretation that dissolves the measurement problem by changing the very nature of what we think a probability is. The central pillar of cubism is a profound shift in perspective. In most interpretations, the probability of an event, say, a 50% chance an electron will spin up, is treated as an objective feature of the universe, a property inherent to the particle itself. Cubism rejects this entirely. It argues that quantum probabilities are not out there in the world, they are inside our heads. They are subjective, Bayesian degrees of belief. That 50% isn't a fact about the electron. It's a statement about your expectations, your personal confidence level that you will have a particular experience upon making a measurement. It is the gambling odds you would assign to the outcome based on your current knowledge. In this view, the revered wave function is not a physical wave or a description of multiple realities. It is simply a mathematical capsule that encodes an agent's personal beliefs and expectations about their future interactions with the world. This transforms every quantum experiment from an investigation into nature's secrets into a process of personal belief updating. When you set up an experiment and calculate a wave function, you are essentially placing a bet on what you will experience when you look at the result. When you then perform the measurement and get an outcome, that experience, that click of the detector, that flash on the screen forces you to radically update your personal beliefs. Your wave function doesn't collapse because the universe changes. It collapses because your state of knowledge changes in a sudden, irreversible jump. The world itself just is. The quantum weirdness is all in our attempt to make sense of it and predict what it will show us next. This approach elegantly sidesteps the traditional paradoxes. There is no measurement problem because the wave function was never a real thing that needed to collapse. Schrödinger's cat is not both dead and alive. It is simply either dead or alive, and you, the agent, hold a set of beliefs about which state you will find. The infamous Wigner's friend thought experiment, where one observer's measurement seems to collapse reality for another, is also resolved. In cubism, each observer is their own separate agent. Your friend's measurement inside the lab updates their personal wave function. For you, outside the lab, your wave function still reflects your uncertainty about what your friend saw. When they open the door and tell you the result, you then update your own beliefs. There is no single objective reality. There is only a collection of individual perspectives, each with their own internal catalogue of expectations and experiences. Cubism offers a deeply pragmatic and human-centered view of science. It says that quantum mechanics is not a theory about what the world is, it is an empirically discovered set of rules that tells us how to best navigate the world and manage our uncertainty about it. It is a tool for decision-making, incredibly powerful and accurate, but not a direct map of an objective territory. This can be liberating. It frees us from searching for a mythical, observer-independent reality, and instead focuses on the incredible success we have in using these rules to interact with and shape our environment. It suggests that the universe is not a puzzle to be solved, but a complex and surprising conversation in which we are all active participants, each of us armed with our own personal guidebook, constantly revising our expectations based on the wondrous and unexpected experiences it offers us. But if the quantum realm suggests a multiplicity of realities born from possibility, could there be an even grander, more architectural framework underlying this cosmic profusion? This brings us to one of the most ambitious and mathematically intricate theories in all of physics, string theory, and its stunning proposal for a multiverse that makes the quantum many-world seem almost quaint in comparison. String theory began as an attempt to solve a fundamental problem: the jarring incompatibility between Einstein's theory of gravity, which paints the cosmos on a vast, smooth canvas, and quantum mechanics, which describes a frenetic, fuzzy subatomic world. To bridge this divide, theorists proposed a revolutionary idea. What if the fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, vibrating strings? These one-dimensional threads, trillions of times smaller than an atom, oscillate at different frequencies, and each distinct vibration pattern gives rise to a different kind of particle. One note on the string might be an electron, another a photon, another a quark. In this elegant vision, the entire symphony of matter and energy is composed from the music of these strings. Yet, for this beautiful mathematics to work, it demands something extraordinary. These strings cannot vibrate in just the 3 dimensions of space and 1 of time that we experience. They require extra dimensions, tiny, curled up, hidden geometries all around us. Initially, physicists hoped there would be one unique way to curl up these dimensions, one specific Calabi-Yau shape that would yield a unique set of physical laws matching our universe. But as research progressed, a shocking realization emerged. The number of possible ways to compactify these extra dimensions is not 1 or 10 or 1,000. It is astronomically vast, perhaps as high as 10 to the power of 500. This is not just a big number, it is a number so incomprehensibly large that the total number of atoms in the observable universe is utterly insignificant by comparison. Each of these different configurations produces a universe with a different set of physical constants, a different strength for gravity, a different mass for the electron, a different value for the cosmological constant. This is the infamous landscape of string theory, a sprawling, arid plain of possibilities where an almost infinite number of different universes could, in principle, exist. This is where the theory dovetails breathtakingly with the concept of the multiverse. In this view, our universe, with its specific, life-permitting constants, is not special or designed. It is simply one possible outcome among an almost endless array of alternatives. It is one bubble in a ceaselessly frothing cosmic foam, a process known as eternal inflation. The idea is that the fabric of spacetime is itself subject to quantum fluctuations, constantly bubbling with new universes that inflate into existence, each with its own random set of physical laws dictated by the accidental pinning of its string theory landscape. Most of these universes would be stillborn, perhaps with gravity so strong that everything instantly collapses into black holes, or with nuclear forces too weak to ever form atoms. They would be chaotic, empty, or simply barren. But in a multiverse of such unimaginable scope, it becomes statistically inevitable that a few bubbles, by pure chance, will have the perfect Goldilocks-style balance of forces necessary for galaxies, stars, planets, and life to emerge. We find ourselves in one such fortunate bubble, not because it was made for us, but because we are here to observe it, a modern incarnation of the anthropic principle. String theory, therefore, provides a potential mathematical foundation for the most expansive multiverse imaginable. It's a vision that is at once humbling and exhilarating. It suggests that the fundamental questions of why our universe is the way it is may have a simple yet profound answer, because it can be, and in an infinite ensemble of possibilities, every possible universe must eventually come into being. The search for a single, unique theory of everything gives way to a cosmic landscape of breathtaking diversity, where the very laws of physics are as variable as the environments on a planet. Yet if the mathematical underpinnings of reality suggest a landscape of possibilities, one theory asks a question that strikes at the very core of our existence. What if the reality we perceive isn't foundational at all, but a kind of grand illusion, a computational artifact running on some unimaginably advanced hardware? This is the simulated reality hypothesis, an idea that has leaped from the pages of philosophy and science fiction into serious scientific and technological debate. Its core proposition is as simple as it is dizzying. The universe we inhabit, with all its richness, from the warmth of the sun to the complexity of human consciousness, may not be base reality. Instead, it could be an intricately constructed simulation, a virtual reality so perfect and immersive that its inhabitants, us, are completely unaware of the deception. The argument often begins with a logical extrapolation of our own technological trajectory. Just a few decades ago, the most sophisticated graphics in video games were blocky, pixelated abstractions. Today, we have fully immersive virtual worlds with millions of players interacting in real time within detailed digital environments. If this rate of progress continues, even at a fraction of the pace, a future civilization, perhaps only a few centuries more advanced than our own, could possess computing power so vast that running simulations indistinguishable from reality would be trivial. They might create simulations of their own ancestors, populated by conscious digital beings with fully realized inner lives. Now take that thought one step further. If such a civilization exists, and if it has any desire to run such simulations for research, for entertainment, for historical preservation, then the number of simulated realities would likely vastly outnumber the one base original reality. If that's the case, the odds are overwhelmingly stacked against us being in the original. Statistically, we are almost certainly living in a simulation. This is where the hypothesis makes a fascinating and direct connection to the quantum weirdness we've been exploring. The strange behavior of particles at the quantum level, particularly the role of the observer, has long been a source of mystery. But what if it's not a mystery of physics, but a feature of the source code? In a sophisticated simulation, rendering an entire universe in perfect, unwavering detail at every moment would require unimaginable processing power. It would be incredibly inefficient. A far more elegant programming solution would be to use a form of procedural generation or lazy loading. The simulation wouldn't need to fully render the entire universe all the time. It would only need to calculate and display the parts that are being observed. The moon doesn't need to have a definite position when no one is looking. its location and properties can remain in a fuzzy, uncalculated state, a superposition, until a measurement is made, forcing the simulation to resolve the value and render the outcome. This would perfectly explain the wave function collapse. The act of observation isn't causing a physical collapse. It's a function call that prompts the central processing unit to calculate and return a definitive result, saving immense computational resources. In this light, the famous double-slit experiment takes on a new character. The interference pattern emerges because when no one is measuring which slit the particle went through, the simulation doesn't need to bother calculating it. It can simply assign a probability wave, but when a detector is placed at the slits to observe the path, the simulation is forced to render a definite outcome for that specific event, collapsing the wave function. The uncertainty principle could be seen as a fundamental resolution limit of the simulation, a built-in constraint that prevents us from measuring certain pairs of properties with perfect precision because that level of detail simply isn't stored or calculated. Even the apparent randomness of quantum events could be explained as the output of an incredibly sophisticated, but ultimately deterministic random number generator within the code. This perspective doesn't diminish the reality of our experience. Whether base or simulated, the pain we feel, the love we share, and the stars we wonder at are no less real to us. But it does reframe the deepest questions of existence. The laws of physics are not fundamental truths discovered by brilliant minds. They are the rules of the simulation, the algorithms written by the programmers. The search for a unified theory of everything becomes the search for the underlying source code of the universe. And the unsettling question of who our creators are and why they are running this simulation becomes the ultimate cosmological mystery. It's a theory that transforms the universe from a great, unknowable existence into a potentially knowable creation, albeit one whose creators and purpose remain entirely hidden behind the veil of the rendered world we call home. But if even our reality might be a simulation, what does that imply about the one thing that feels most undeniably real to us, our own consciousness? This leads us to a theory that turns the entire question inside out. Instead of asking how consciousness might emerge from the brain, it asks if consciousness itself might be a fundamental feature of the universe as primary as space and time. This is the theory of panpsychism, and it offers a radical solution to the infamous, hard problem of consciousness, the question of why and how physical processes in the brain give rise to subjective experience, the raw feeling of what it is like to be something. The standard materialist view assumes consciousness is an emergent property, a complex software that somehow boots up from the biological hardware of the brain. But panpsychism challenges this, pointing out that we have no satisfactory explanation for how mere matter arranged in a certain way suddenly sparks an inner life. How do billions of neurons firing create the sensation of the color red, the taste of chocolate, or the feeling of love? This is the explanatory gap that materialism has yet to bridge. Panpsychism proposes a different starting point. What if consciousness isn't something that emerges at a certain level of complexity? What if it's a fundamental property that was always there, inherent in the very fabric of reality itself? In this view, consciousness did not evolve, it was revealed. It didn't appear out of nowhere in complex animals. It was present in some extremely basic form, in the very first particles that came into existence after the Big Bang. Just as an electron has properties like mass and charge, it might also have a tiny, elemental kernel of experience, a minuscule degree of proto-consciousness. This isn't to say an electron is thinking or feeling emotions. Its experience would be unimaginably simple, perhaps just a bare whisper of existence. But when these fundamental particles combine into more complex structures, atoms, molecules, cells, and finally, the intricate neural networks of a brain, these tiny sparks of consciousness combine and amplify, ultimately giving rise to the rich, unified stream of awareness that you and I experience. The brain isn't generating consciousness, it's harnessing and orchestrating it, acting as a receiver or filter for a property that is everywhere. This idea finds a surprising resonance with certain interpretations of quantum mechanics, particularly those that place the observer at the center. If consciousness is fundamental, then its role in collapsing the wave function makes a new kind of sense. It's not that a human brain is magically affecting atoms. It's that consciousness, as a basic ingredient of the universe, is involved in the very process of reality becoming definite. Panpsychism offers a vision of a truly participatory universe, one that is not dead, inert matter, but is in some sense alive and aware at its most fundamental level. It suggests that we are not lonely consciousnesses trapped in a vast, unconscious machine of a cosmos, but rather localized expressions of a universal field of mind, intimately connected to the consciousness inherent in a star, a planet, or even a rock, albeit at a vastly different level of complexity and richness. Yet as startling as the idea of a simulated or conscious cosmos may be, it challenges our assumptions about reality on a deeply philosophical level. But what if the illusion is not one of software or spirit, but of dimension itself? This brings us to a theory so geometrically audacious that it reimagines the very structure of space-time, suggesting that all the richness of our three-dimensional world is nothing more than a magnificent projection, a cosmic illusion. This is the holographic principle, and it proposes that our universe is essentially a hologram, a vast and incredibly detailed three-dimensional image encoded on a distant two-dimensional surface. The seeds of this idea were first discovered in the study of black holes, those ultimate paradoxes of physics. In the 1970s, physicist Jacob Bekenstein and Stephen Hawking made a startling discovery. A black hole's entropy, a measure of its information content, is not proportional to its volume, as one might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon. This was profoundly strange. It suggested that all the information needed to describe everything that ever fell into the black hole, every atom, every person, every planet, could be entirely encoded on the two-dimensional boundary that surrounds it, much like the data on a DVD is encoded on its flat surface and then projected into the three-dimensional image you see on your screen. The three-dimensional interior, in this view, might be a kind of emergent illusion. The holographic principle boldly extends this concept to the entire universe. It suggests that our cosmic horizon, the farthest point we can possibly observe, acts as that two-dimensional surface. Every event, every particle, every force interaction within our observable universe could be described by bits of information stored on this distant, flat boundary. The three-dimensional world we move through, with its galaxies, stars, and people, would then be a projection of that data, a holographic reconstruction. We are not looking at a hologram, we are living inside of one. In this view, the universe doesn't have three spatial dimensions plus time in the fundamental sense. At its most basic level, reality is a two-dimensional information structure, and the third dimension is a derived, emergent property. This is not saying the universe is an illusion in the sense of being fake. It is saying that its apparent dimensionality is not fundamental. This provides a revolutionary framework for unifying the two great pillars of physics, quantum mechanics and general relativity. Gravity, which shapes the cosmos on the largest scales, emerges from the geometric dynamics of this holographic projection. Meanwhile, the quantum information theory that governs the microscopic world operates on the lower dimensional boundary. The principle beautifully resolves the black hole information paradox, the question of what happens to information that falls into a black hole, which quantum theory says must be preserved. If the information is never actually lost inside the singularity, but is instead eternally smeared and preserved on the event horizon, the paradox vanishes. The entanglement of quantum particles, that spooky connection that Einstein disliked, might be the fundamental glue that stitches together the projected reality we experience, connecting points on the boundary to create the seamless illusion of a continuous three-dimensional space. In this breathtaking vision, the universe is not a collection of things but a network of information relationships, a cosmic code whose output is the stunningly realistic reality we call home. While string theory adds extra dimensions to smooth out the wrinkles in our understanding, another approach tackles the problem from the opposite direction, proposing that the solution isn't more dimensions, but a fundamental reimagining of the dimensions we already have. This rival framework is known as loop quantum gravity, and its core premise is as radical as it is elegant. Space itself is not a smooth, continuous backdrop. Instead, it is woven from a fabric of incredibly tiny, discrete, interconnected loops, a network of finite threads of gravity. This is a theory that doesn't try to force quantum mechanics and gravity to get along. It rebuilds gravity from the ground up using quantum rules, and in doing so, it paints a stunning new picture of the cosmos where nothing, not even nothingness, is truly continuous. Imagine you are looking at a beautifully woven Persian rug. From a distance, the image appears seamless, a continuous flow of color and pattern. But if you lean in close, right up to the fibers, you see the truth. The image is composed of countless individual threads tied together in an intricate network. There is a smallest possible unit of the weave. You cannot have half a knot. Loop quantum gravity proposes that the fabric of spacetime is exactly like that rug. What we perceive as the smooth, empty void of space is, at the unimaginably small Planck scale, a dense, dynamic tapestry of these one-dimensional loops of gravitational field, all knotted and linked together. Space is not infinitely divisible. It comes in discrete, quantized packets. There is a smallest possible unit of volume, a true atom of space. This granularity solves some of the most vexing problems in physics. Take the black hole singularity, that point of infinite density where Einstein's equations break down and our laws of physics scream in protest. In the loop quantum view, the collapse of matter cannot reach zero volume because space itself is granular. There is no smaller than the smallest possible volume. The crushing gravity of a collapsing star would therefore meet a cosmic repulsive force generated by the quantum nature of space itself, causing the matter to bounce back rather than vanish into an infinitely dense point. Similarly, this theory offers a breathtakingly beautiful resolution to the origin of the universe. The Big Bang may not have been a singularity, a true beginning from nothing, but rather a big bounce. A previous universe may have contracted to a point of immense density, but then, pushed by the quantum graininess of space, rebounded outward in the expansion we see today. Our cosmos, in this view, could be one in an endless cycle of contraction and expansion, a phoenix forever rising from its own ashes. The visual picture this theory provides is profoundly different from the strings and brains of its competitor. The universe, according to loop quantum gravity, is often called a spin network, a constantly evolving web of relationships where each intersection point represents a tiny volume of space and each link represents a quantum of area. Time itself emerges from the changing relationships between these nodes. This is a universe where geometry is everything, and matter is not something that exists in space, but is rather a property of this woven geometry, a particular excitation of the loops themselves. It's a vision that is both austere and deeply relational, suggesting that the properties of location and distance are not fundamental but derive from the connections in this underlying network. Where string theory offers a vast landscape of possible universes, loop quantum gravity strives for uniqueness, aiming to describe our specific universe from first principles without free parameters. It is a theory that many find more philosophically satisfying because it does not invoke unobservable extra dimensions. It works directly with the three spatial and one-time dimension we experience. Yet it faces its own immense challenges, particularly in finding ways to connect its abstract, mathematical description of quantized space to the familiar, smooth reality we see and test in our experiments. Both theories represent monumental acts of human imagination, two very different paths up the same mountain, each offering a radically different yet equally compelling vision of the quantum heart of reality. But if the holographic principle suggests our reality is a projection and quantum theory places such weight on observation, could it be that observers like us are not merely incidental products of the universe, but essential participants in its very creation? This brings us to an idea that stands as one of the most profound and mind-bending in all of cosmology: the participatory anthropic principle, championed by the legendary physicist John Archibald Wheeler. He took the standard anthropic principle, the simple observation that our universe must be compatible with life because we are here to observe it, and turned it into something far more radical and active. Wheeler proposed that we don't just inhabit a life-friendly universe, we help create it through the very act of observation, retroactively shaping the entire cosmic history that led to our existence. Wheeler was deeply troubled by the role of the observer in quantum mechanics, famously asking if the universe could Chinese letter in some real sense without ever being observed. His answer, developed over decades, was a resounding no. He envisioned a cosmos that only achieves definite reality when it is observed, a concept he called a self-excited circuit. In this view, the universe brings itself into being through acts of observation that are distributed across time and space. The most stunning expression of this idea is his thought experiment, delayed choice experiment, which pushes the weirdness of the quantum world to its absolute limit. Imagine a distant quasar, a brilliant beacon of light billions of light years away. Its light travels toward Earth, and on its journey, it is gravitationally lensed by a massive galaxy. It splits into two paths that travel around either side of the galaxy before converging and continuing onto our telescopes. Now, according to quantum mechanics, an individual photon from that quasar must have taken both paths simultaneously, creating an interference pattern that we could, in principle, detect. But suppose we set up a device at our telescope that can detect which specific path each photon took. The moment we do that, the interference pattern vanishes. Each photon behaves as if it chose a single, definite path billions of years ago. Wheeler's genius was to ask, what if we wait until after that photon has already finished its multi-million-year journey and is just about to hit our detector before we decide which experiment to perform? Astonishingly, the result is the same. If we choose to measure the path, the photon acts like a particle that took one path. If we choose to look for interference, it acts like a wave that took both paths. Our decision now seems to affect what that photon did billions of years in the past. This isn't science fiction. Versions of this experiment have been conducted in laboratories, and the results confirm Wheeler's prediction. The implications are staggering. They suggest that the past is not fixed and determinate. It is waiting to be actualized by measurements made in the present. The universe's history is not a set of carved stone tablets. It is a living, breathing story whose earlier chapters are not yet written until later events compel them into being. In Wheeler's participatory universe, we are not passive audience members watching a cosmic film whose ending is already known. We are active co-authors, and the choices we make today, the questions we ask of nature, are writing the opening scenes of the cosmic story retroactively. The Big Bang itself may not have been a definite event until its consequences, namely conscious observers like us, emerge to look back and give it a concrete meaning. This transforms our understanding of our place in the cosmos. Life and consciousness are not accidental flickers in a vast, indifferent machine. They are fundamental players, the means by which the universe comes to know itself and achieves reality. The long chain of cosmic evolution, the formation of galaxies, the forging of heavy elements in stellar furnaces, the accidental assembly of self-replicating molecules on a tiny planet. All of it was a set of possibilities, a tapestry of potential histories. It was only with the arrival of observers capable of measuring and questioning that this vast potential suddenly crystallized into the specific, actual history we now call our own. We are participants in a grand cosmic circuit, and our observation is the final link that closes the loop, allowing the universe to truly exist. It is a vision that bestows upon us a breathtaking responsibility, suggesting that through our curiosity and our quest for knowledge, we are quite literally bringing the cosmos into being. Yet for all the strange beauty of these interpretations, a stubborn question remains. If the universe is fundamentally quantum, a blurry superposition of possibilities, then why does it appear so solid, stable, and most importantly, so agreed upon to all of us? Why do we all see the same moon in the sky? If reality is a matter of perspective, as cubism suggests, or a matter of branches, as many worlds proposes, how do we all manage to share a single, consistent version of events? This is the puzzle of the quantum to classical transition, and a compelling answer emerges not from fundamental physics, but by borrowing a powerful idea from biology. This is quantum Darwinism, a theory that proposes objective reality isn't given. It is forged through a process strikingly similar to natural selection. The central insight of quantum Darwinism is that not all quantum information is created equal. When a quantum system interacts with its environment, which it is constantly doing as we learn from decoherence, it imprints information about itself onto the countless particles in its surroundings. But it doesn't imprint every possible detail. Think of a red apple sitting on a table. The apple is a quantum object, a complex collection of particles that, in principle, could be in a superposition of positions. But it isn't. Its location is definite. Why? Because it is constantly being struck by photons of light, which bounce off it and carry information about its position out into the world. Crucially, the apple's specific shade of red, or the exact quantum state of its atoms, is fragile information that gets scrambled and lost in these interactions. But its position, the fact that it is here and not there, is an extremely stable, robust piece of information. That particular state is able to withstand the bombardment and gets copied over and over again into the environment. This is the process of survival of the fittest information. The environment acts as a probing, measuring mechanism that constantly tests the quantum system. Only the most stable, redundant, and useful information survives this process and gets widely disseminated. These stable states are known as pointer states, and they are the quantum equivalent of a species perfectly adapted to its niche. In the case of the apple, its pointer state is its location. That information is replicated into trillions of photons, which then travel to your eyes, to a camera, to any other object in the room. Anyone or anything that comes along to measure the apple will inevitably access this same, widely copied information. They will all agree the apple is on the table. The subjective experience of each observer is based on measuring the same objective data etched into the environment. This elegantly explains why we all share a common reality. We are not all directly collapsing the wave function of every object we see. Instead, we are all simply reading from the same cosmic bulletin board, a bulletin board that has been updated by the process of environmental monitoring. The environment itself performs a continuous, unconscious measurement, and we, as observers, merely tap into the results that have already been redundantly published. This makes objective reality an emergent property. It emerges from the countless interactions between a quantum system and its surroundings, which selectively amplify only certain information and discard the rest. The world appears classical and definite not because the quantum weirdness is gone, but because the weird, fragile superpositions are constantly being measured out of existence by the environment, leaving behind only the most durable, copyable facts for us to discover. In this view, the solidity of the world is a consensus reached by the universe itself, a consensus we are privy to simply by being a part of it. But even as we grapple with the nature of reality on a cosmic scale, some of the most intense battles in theoretical physics are fought over the most extreme objects in the universe, black holes. These gravitational monsters seem to play by a different set of rules, and at their edge, the two great pillars of modern physics, quantum mechanics and general relativity, clash in a conflict so fundamental it threatens to unravel our entire understanding of the cosmos. This is the black hole information paradox, a puzzle that asks a deceptively simple question. When something falls into a black hole, is all information about it lost forever? The answer to this question forces us to confront the very nature of reality, information, and whether the universe is fundamentally reversible or not. To understand the paradox, we first need to understand what physicists mean by information. This isn't about books or hard drives. In this context, information refers to the unique quantum identity of every particle. It's the complete set of properties that make one electron different from another. Its spin, its momentum, its energy state. The core principle of quantum mechanics is that this information is never destroyed. It can be scrambled, mixed, and transformed into incredibly complex forms, but it can never be truly erased. This principle of unitarity is the bedrock of quantum theory. It ensures the universe is predictable and that the past always leaves a recoverable trace. Now enter the black hole as described by Einstein's general relativity. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape its pull once it crosses the boundary known as the event horizon. If you throw a book, or indeed an entire encyclopedia, into a black hole, general relativity says it is gone. It is irretrievably crushed into the singularity at the center, a point of infinite density where the laws of physics cease to exist. According to this pure classical view, all the information contained in that encyclopedia is lost forever. This creates a direct contradiction with quantum mechanics, setting up the central paradox. The conflict deepened immeasurably when Stephen Hawking made a revolutionary discovery in the 1970s. By applying quantum theory to the space just outside a black hole's event horizon, he showed that black holes are not completely black. They should slowly leak a faint glow of radiation, now famously known as Hawking radiation. This radiation is generated when pairs of virtual particles, a particle and its antiparticle, pop into existence from the quantum foam near the event horizon. Normally, these pairs annihilate each other almost instantly, but if they appear right at the horizon, one particle can fall in while the other escapes, stealing a tiny amount of energy from the black hole's gravitational field. This process causes the black hole to gradually lose mass and over eons evaporate completely until it vanishes in a final burst of energy. Hawking's calculation was a stunning triumph, but it came with a devastating catch. He determined that this Hawking radiation is purely thermal. It is random noise, like the heat radiating from a stove. It contains no information whatsoever about the specific things that fell into the black hole. So the black hole evaporates, leaving behind only this featureless thermal radiation. The original information, the quantum states of every star, planet, or book that ever fell in appears to have been completely erased from the universe. This information loss violates the most sacred rule of quantum mechanics. It would mean the universe is not unitary. The past is not just hidden but obliterated. As physicist John Preskill put it, it would mean that what happens inside a black hole stays inside a black hole permanently and completely. Hawking himself famously bet against information preservation, convinced his calculations showed it was truly lost. For decades, this was the stalemate. Quantum mechanics said information must be preserved. Hawking's application of quantum mechanics to black holes said it was destroyed. This was more than a technical disagreement. It was a sign that our foundational theories were fundamentally incompatible at the most extreme scales. Resolving this paradox became the single most important goal for a generation of theoretical physicists. The solution, many believed, would require a theory of quantum gravity, a way to seamlessly merge the rules of the very small with the rules of the very dense. One of the most prominent attempts to resolve the paradox is the idea of black hole complementarity, proposed by Leonard Susskind and others. This ingenious idea suggests that the information is both lost and not lost depending on your perspective, and that no single observer can ever see the contradiction. For an observer watching from a safe distance outside the black hole, the information never actually crosses the event horizon. Instead, it gets smeared and encoded onto the horizon itself, a concept that resonates with the holographic principle. This observer would then see that information slowly and encodedly radiated back out via the Hawking radiation. From this outside perspective, information is preserved. However, for an astronaut foolish enough to dive into the black hole, the story is different. According to general relativity, they would pass smoothly through the event horizon, noticing nothing special at that point, and would eventually be spaghettified and crushed at the singularity. From their perspective, the information goes with them into the singularity. So, is the information inside or on the surface? Complementarity says both descriptions are correct simultaneously for their respective observers. The laws of physics simply prevent any one observer from ever collecting both sets of information to prove a contradiction. It's a cosmic version of he said, she said, where the universe ensures the two stories can never be compared. But this elegant solution was itself challenged by a further thought experiment, leading to an even more radical and violent proposal, the firewall paradox. If black hole complementarity is correct and the Hawking radiation carries the information of what fell in, then it must be entangled with the particles that fell into the black hole. But quantum mechanics also demands that the Hawking radiation particles are entangled with each other in a specific way. This creates a problem. A fundamental rule of quantum mechanics called the monogamy of entanglement states that one particle cannot be fully entangled with two different systems. The argument goes that by the time the black hole is halfway through its evaporation, the radiation outside must somehow be entangled with both the early radiation and with the particles inside the hole, a clear violation of the rule. To resolve this new paradox, physicists Ahmed Almary, Donald Marolf, Joe Polchinski, and James Sully argued that the only way out is to sever the entanglement at the event horizon. But breaking quantum entanglement requires an immense amount of energy. The consequence is that the event horizon would not be the smooth, peaceful gateway described by general relativity. Instead, it would be a blazing wall of high-energy particles, a firewall, that would instantly incinerate any astronaut trying to cross it. This was a shocking suggestion, as it meant that the event horizon, a place Einstein's equations describe as unremarkable, is actually the most violent and destructive place in the universe. The firewall paradox essentially tells us that we cannot have all three things we hold dear: the smoothness of the event horizon, the unitary preservation of information, and the standard rules of quantum field theory. At least one of them must be wrong. The debate rages on, with new ideas constantly emerging. Some theories suggest the information is stored in a remnant, a tiny, incredibly dense leftover after the black hole evaporates. Others propose that our understanding of entanglement itself needs a radical overhaul. What makes the black hole information paradox so profound is that it is no longer just about black holes. It has become a powerful lens through which we are forced to examine the deepest connections between quantum information, gravity, and the very fabric of space-time. The resolution, when it finally comes, will not just tell us what happens to stuff that falls into a black hole. It will reveal a fundamental truth about how the universe manages and preserves the data of its own existence. writing the final chapter on whether reality is ultimately knowable or forever shrouded in mystery. For all the strangeness we've encountered, from branching worlds to holographic projections, the universe as we understand it still feels fragmented. The forces that govern it, gravity, electromagnetism, the strong and weak nuclear forces, are described by entirely different sets of rules. Gravity sculpts the cosmos on the grandest scales through the bending of space-time, while the quantum forces choreograph the frantic dance of particles. Uniting these disparate rulebooks into a single, elegant framework is the holy grail of modern physics, and one of the most promising paths toward that unification is a theory of breathtaking mathematical beauty and profound implication: supersymmetry. At its heart, supersymmetry, often nicknamed SUSY, proposes a fundamental partnership at the core of reality. It suggests that for every known particle in the universe, there exists a hidden superpartner particle. This isn't just a random doubling of the cosmic inventory. It's a deep and powerful symmetry that would fundamentally rewrite our understanding of the quantum world. The known particles are divided into two great families, fermions and bosons. Fermions, like electrons and quarks, are the stubbly, antisocial building blocks of matter. They are what you, the planets, and the stars are made of. Bosons, like photons and gluons, are the gregarious force carriers. They are the messengers that shuttle between matter particles, telling them how to interact. Supersymmetry proposes a perfect one-to-one correspondence between these two families. For every matter particle, a fermion, there should be a force carrying superpartner, a S-fermion, like a squark or selectron. And for every force carrier, a boson, there should be a matter-like superpartner, a bosino, like a photino or gluino. This elegant swap would bridge the great divide between matter and force, suggesting they are two sides of the same coin, different vibrational modes of a more fundamental substance. It's a symmetry so profound it would make the universe's underlying mathematics far more beautiful and stable, resolving many of the thorny mathematical inconsistencies that plague our current models. Perhaps the most compelling implication of supersymmetry is its potential to solve the mystery of dark matter. Our observations of galaxies show they are spinning so fast that they should fly apart, yet something invisible, a huge halo of unseen matter, is providing the extra gravity to hold them together. This dark matter must be stable, electrically neutral, and barely interact with ordinary matter. The lightest superpartner particle, or LSB, is a perfect candidate. Many versions of SUSY predict that a particle like the neutralino, a stable, heavy, neutral mix of superpartners, could have been created in abundance during the Big Bang and simply drifted through the cosmos ever since, forming the invisible scaffolding upon which galaxies are built. Finding evidence for SUSY wouldn't just add new particles to a chart. It would finally illuminate the 95% of the universe that currently lies in shadow. For decades, physicists were confident we would soon discover this hidden symmetric layer. The mathematics were so compelling, the theoretical benefits so enormous that SUSY felt inevitable. Powerful particle colliders like the Large Hadron Collider were built with the expectation of finding these superpartners. The principle seemed straightforward. If you smash ordinary particles together with enough energy, you should be able to shake loose their heavier superpartners from the quantum foam. Yet so far, the detectors have remained silent. No squarks, no leptons, no photinos have appeared. This absence is a profound puzzle. It doesn't mean supersymmetry is wrong, but it suggests the theory is more subtle than we first imagined. The superpartners must be far heavier than initially hoped, perhaps existing at energy scales our current technology cannot yet reach, or they might be hiding in complex ways that make them difficult to produce and detect. This experimental silence forces us to confront a deeper question about the nature of reality and our place within it. Supersymmetry implies a cosmos of perfect balance and harmony, a universe singing in a key we cannot yet hear. The fact that we don't see this symmetry in our everyday, low-energy world suggests it is a broken symmetry. Much like a perfectly symmetric seed grows into a tree that branches in asymmetric ways, the universe may have begun in a state of perfect supersymmetry that was lost as it cooled and expanded. We are living in the aftermath of that breaking, in a frozen, asymmetric state where the beautiful underlying order is hidden from view, detectable only through its subtle echoes in the mathematics of particle physics and the gravitational pull of dark matter. It remains one of the most elegant and promising ideas in all of science, a theory that continues to guide our search for a deeper, more unified, and more symmetric reality. This astonishing possibility brings us to a theory that reads like the most daring science fiction, yet emerges from the pens of some of the most respected minds in theoretical physics. It's called the ER=EPR conjecture, and it proposes a breathtakingly elegant connection between two of Einstein's most revolutionary, yet seemingly unrelated ideas. On one hand, we have the EPR paradox, named for Einstein, Podolsky, and Rosen, which describes the spooky, instantaneous connection of quantum entanglement. On the other, we have the ER bridge, or Einstein-Rosen bridge, which is the formal name for a wormhole, a hypothetical tunnel through the fabric of spacetime itself. The conjecture, most famously advanced by physicists Juan Maldacena and Leonard Susskind, proposes a wild and beautiful idea. These two concepts are not just analogous, they are one and the same. An entangled pair of particles, they suggest, is not mysteriously linked across a vast distance. They are actually connected by a microscopic wormhole. To grasp the sheer brilliance of this, we need to revisit the two halves of this cosmic equation. Quantum entanglement, the EPR part, is that bizarre phenomenon where two particles become so deeply linked that measuring the state of one instantly determines the state of the other, no matter how far apart they are separated. Einstein famously derided this as spooky action at a distance because it seemed to violate the cosmic speed limit of light. It presents a universe that is deeply interconnected in a way that defies our classical intuition about locality and separation. A wormhole, the ER part, is a shortcut through the universe, a tunnel that connects two distant points in spacetime. If you could traverse it, you could theoretically travel from one point to another faster than light could traveling the long way around through normal space. General relativity allows for such structures, though they are typically thought to be unstable and require exotic forms of matter to hold them open. The ER=EPR conjecture boldly states that these two ideas are two different descriptions of the same underlying reality. When we say two particles are entangled, we are not describing a mysterious, non-local correlation. We are, in fact, describing a tiny, Planck-scale wormhole that physically connects them. The spooky action at a distance isn't spooky at all, it's geometric. The particles are able to influence each other instantly because they are not truly separate. They are two mouths of the same tiny tunnel. The information about their states isn't teleporting across a void. It is simply taking a shortcut through a hidden extra dimension of spacetime. This reframes entanglement not as a fragile quantum connection, but as a physical bridge, a feature of the very geometry of the universe. This idea is more than just a poetic unification. It offers a potential pathway to resolving the greatest conflict in modern physics, the chasm between quantum mechanics and general relativity. The black hole information paradox we discussed is a direct manifestation of this conflict. ER=EPR provides a stunningly elegant potential solution. Imagine a pair of entangled particles. One falls into a black hole while the other remains outside. According to standard quantum mechanics, the particle outside remains entangled with its partner inside, but this seems to lead to the firewall paradox we explored. However, if entanglement is equivalent to a wormhole, then the moment one particle falls in, the microscopic wormhole connecting them stretches and evolves, tethering the external particle directly to the interior of the black hole. The information about the infalling particle isn't lost or trapped. It is accessible from the outside via this wormhole link, potentially resolving the paradox by preserving information without the need for a violent firewall. The implications stretch far beyond black holes, painting a radical new picture of the universe's architecture. It suggests that the seemingly empty space around us might be teeming with an unfathomably complex network of these microscopic wormholes, a vast, invisible web of space-time connections that underlies all quantum correlations. The fabric of reality itself might be built from this subatomic stitching. This vision transforms the universe from a collection of separate objects floating in a void into a deeply interconnected network, a cosmic labyrinth where every entangled connection is a physical thread in the tapestry of spacetime. It's a theory that dares to suggest that the most fundamental laws of physics, those governing information and those governing gravity, are ultimately and beautifully the same. But what if the very idea of a particle is a kind of mirage, a convenient label we use for something far more fundamental and strange? This brings us to a framework that is arguably the most successful and accurate scientific theory ever devised. A theory that doesn't just describe the universe, but redefines what the universe is made of. This is quantum field theory, and it proposes a reality so dynamic and fluid that it makes the previous theories seem almost static by comparison. Forget thinking of the universe as filled with tiny, solid balls called particles. Instead, imagine an infinite, invisible ocean that fills all of space and time. This ocean is not made of water, but of something more abstract: fields. There is an electron field, a quark field, a photon field, a different field for every type of fundamental particle in nature. These fields are not mere abstractions, they are the primary substance of reality. What we perceive as a particle is nothing more than a localized ripple, a tiny excitation in this underlying field. An electron is simply a place where the electron field is vibrating in a particular way. A photon is a knot of energy traveling through the electromagnetic field. In this view, particles aren't things that exist in space, they are manifestations of the fields that are space. This shift in perspective resolves one of the oldest puzzles in quantum mechanics: wave-particle duality. There is no duality, there are only fields. Sometimes these fields behave in a wave-like manner, spreading out and interfering. Sometimes they behave in a particle-like manner, interacting at a point. But it's all just the same field, expressing itself in different ways depending on how we choose to poke it. The famous double-slit experiment is recast not as a paradox of particles being waves, but as a clear demonstration of a field's wave nature. The electron field vibrates, its waves pass through both slits, interfere, and that pattern of interference tells the field where the electron is most likely to manifest as a particle-like excitation when it hits the detector. The most astonishing implication of this framework is what it says about emptiness. We think of a vacuum as pure nothingness, a void completely devoid of matter and energy. But according to quantum field theory, a vacuum is the exact opposite. It is alive with frantic, seething activity. Because these quantum fields are everywhere and always on, they are subject to the uncertainty principle, even in their lowest energy state. This means the value of a field at any point in space can never be exactly zero. It is constantly fluctuating. These fluctuations are not just mathematical quirks, they have real, measurable physical consequences. For incredibly brief moments, these fluctuations can borrow energy from the universe to create pairs of virtual particles, a particle and its antiparticle, that spontaneously pop into existence and then almost immediately annihilate each other, paying back the energy loan before it can be detected directly. This is not a theory, it is a tested and verified phenomenon. The Casimir effect, for instance, demonstrates this beautifully. If you place two incredibly smooth metal plates extremely close together in a vacuum, they will be gently pushed toward each other. Why? Because the space between the plates is so narrow that only certain wavelengths of virtual particles can pop into existence there, while outside the plates all wavelengths can appear. The greater pressure from the outside virtual particles pushes the plates together, a clear, measurable force generated by the energy of empty space itself. This means the very vacuum we float in is a bubbling soup of transient particles, a quantum foam where existence is a constant dance of creation and destruction. The atoms that make up your body, the screen you're looking at, the air you breathe, all of it is just a relatively calm pattern atop this unimaginably energetic quantum substrate. You are not looking out at the universe from a place of stillness. You are a stable vibration in a field, riding atop an ocean of infinite potentiality whose constant churning is the true engine of reality. This dynamic vacuum energy might even hold the key to one of cosmology's greatest mysteries: dark energy, the mysterious force causing the universe's expansion to accelerate. It's possible that the energy of these vacuum fluctuations is the source, though the calculated value is famously off by a staggering factor of 10 to the power of 120. This discrepancy tells us that while quantum field theory is magnificently powerful, there is a deeper layer of reality we have yet to uncover, a layer where the true nature of the vacuum awaits our discovery. For all the grandeur of these cosmic theories, the most persistent and perplexing mystery remains right here in the laboratory, confronting us every time we try to measure the quantum world. This is the measurement problem, the central, unresolved puzzle that lies at the heart of quantum mechanics. It's a problem so fundamental it asks what it even means for something to be real. We know a particle can exist in a blurry superposition of states, like being in two places at once. The mathematics of the wave function describes this blend of possibilities perfectly. But the moment we set up a detector to look, that delicate superposition seems to vanish, collapsing into a single, definite outcome. The question is, what exactly triggers this collapse, and why does the mere act of observation have such a profound power over reality? This isn't just a philosophical debate, it's a concrete problem with experimental consequences. The Copenhagen interpretation, as we've discussed, places the observer at the center of this drama, suggesting that consciousness itself is the mysterious ingredient that forces the quantum world to make up its mind. But this raises a host of difficult questions. Where do we draw the line? Does a photomultiplier tube count as an observer? What about a cat or a bacterium? The theory provides no clear boundary between the quantum realm of possibility and the classical world of fact, leaving us with a universe that seems to require a conscious mind to complete it. This ambiguity is brilliantly highlighted by a thought experiment known as Wigner's friend, devised by physicist Eugene Wigner. Imagine his friend is inside a sealed laboratory, performing a quantum experiment on a single particle in superposition, say, measuring its spin. From the friend's perspective inside the lab, they make the measurement and get a definite result. The wave function for them has collapsed, but now Wigner is outside the closed door. From his perspective, the entire laboratory, including his friend and all the equipment, must be treated as a single quantum system. That entire system is now in a monstrous superposition of states, one where his friend measured spin up and is happy, and another where his friend measured spin down and is disappointed. For Wigner outside, the wave function hasn't collapsed until he opens the door and asks his friend what happened. So, who is right? When did the collapse really occur? Was it when the friend looked or when Wigner got the report? This paradox suggests there is no objective reality, only a patchwork of subjective experiences, and it pushes the role of consciousness to its absolute limit. Other interpretations offer their own solutions, each with unique implications. The many worlds interpretation, for instance, sidesteps the problem entirely by declaring that collapse is an illusion. There is no sudden jump to a single state. Instead, the observer becomes entangled with the system, and the entire universe branches. Wigner and his friend both split, each experiencing a different, equally real outcome. The transactional interpretation, with its waves handshaking across time, sees the measurement as the finalization of a deal between the future and the past. And quantum Bayesianism, cubism, dissolves the problem by declaring the wave function isn't a real thing but a personal catalog of beliefs. The collapse is just you updating your expectations based on new experience. Modern experiments are now putting these ideas to the test in increasingly sophisticated ways by creating larger and larger objects in superposition. From molecules to tiny vibrating drums, physicists are probing the elusive boundary where quantum behavior supposedly gives way to classical certainty. The emerging understanding from decoherence shows that the environment is constantly performing involuntary measurements, but this still doesn't pinpoint the exact moment a single outcome is chosen from the menu of possibilities. The measurement problem, therefore, endures not as a flaw in the mathematics, which works perfectly, but as a deep mystery about the nature of reality itself. It forces us to ask whether our classical intuition about a single, objective world is a convenient fiction, and if the true nature of existence is far more fluid, participatory, and dependent on the questions we choose to ask. But this seemingly magical connection holds a crucial catch, one that prevents it from being the ultimate cosmic cheat code for faster-than-light communication. While the state of one particle is instantly correlated with its partner, this correlation is completely random and cannot be controlled or manipulated from the outside. Imagine you and a friend each have one of a pair of magic coins that are forever linked. The moment you flip your coin and see it land on heads, you know instantly that your friend's coin has landed on tails. That knowledge is instantaneous, transcending space. However, you had no control over whether your coin would be heads or tails. You cannot force your coin to be heads in order to send a deliberate signal to your friend. The outcome is random for both of you, and it's only after comparing your results through a conventional, slower-than-light method like a phone call that you both realize the spooky correlation was there all along. This is why quantum entanglement cannot be used to send messages faster than light. It transmits correlation, not controlled information. The universe, it seems, allows for this profound connectedness while rigorously enforcing a cosmic censorship on causality, ensuring that cause and effect never break the light-speed barrier and that the fundamental order of time remains intact. The mechanism that brings this astonishing possibility into the realm of practical science is a protocol known as quantum teleportation. This isn't the teleportation of science fiction, where a person is dematerialized in one place and reassembled in another. Instead, it is the teleportation of information, the exact quantum state of a particle. Here's how this remarkable process works. Let's say Alice wants to teleport the quantum state of a photon she has to Bob, who is on the other side of the planet. First, Alice and Bob must share a pair of entangled particles which act as their quantum link. Alice then takes her original photon and performs a special joint measurement on it and her half of the entangled pair. This measurement entangles her two particles and, crucially, causes her original photon's quantum state to be destroyed, a necessary step dictated by the quantum no-cloning theorem, which states that an unknown quantum state cannot be copied. The incredible part is what happens next. The moment Alice performs her measurement, Bob's entangled particle, thousands of miles away, is instantly projected into a new state. However, this new state isn't yet a perfect copy of the original. It's a transformed version. The act of Alice's measurement produces a classic result, a simple piece of information like 2 bits of data, 1 or 0, 1 or 0. She must then send this ordinary information to Bob over a standard classical channel, like a radio wave or an internet connection, which of course is limited by the speed of light. Once Bob receives this classical message, He knows exactly what operation to perform on his own entangled particle to transform its state into a perfect replica of the original photon that Alice destroyed. The truly non-local part, the spooky action, was the instantaneous change in Bob's particle the moment Alice measured. But without that slower-than-light classical message to decipher it, the information on Bob's end is just random noise. This beautiful dance between the instantaneous weirdness of quantum entanglement and the plodding certainty of classical communication is what makes quantum teleportation possible, a stunning demonstration that the universe uses both spooky and ordinary channels to manage information. The implications of this for the future of technology are nothing short of revolutionary, paving the way for a quantum internet. This wouldn't be a faster internet for streaming videos. It would be an entirely new network with unhackable security guaranteed by the laws of physics themselves. Quantum key distribution allows two parties to create a secret encryption key using entangled particles. Any attempt by an eavesdropper to intercept the key would inevitably disturb the delicate quantum states, alerting the legitimate users to the presence of an intruder and causing the compromised key to be discarded. Beyond security, a quantum internet could connect future quantum computers into a powerful distributed network, allowing them to solve problems that are completely intractable for any classical machine. We are already witnessing the dawn of this technology, with researchers successfully teleporting quantum states between different labs in separate cities, and even from the ground to a satellite in orbit, building the very first links in a global web that operates on the principles of quantum entanglement. On a deeper, more philosophical level, the phenomenon forces us to confront the very nature of space and time. Einstein's theory of relativity cemented the idea of locality, the principle that objects can only be influenced by their immediate surroundings, and that any influence must travel through space at a finite speed. Quantum entanglement shatters this comfortable view, suggesting that the universe is fundamentally non-local. Entangled particles behave as if the space between them doesn't exist, as if they are a single entity. This has led some physicists to propose that space itself may not be a fundamental stage but an emergent property that arises from a vast underlying network of quantum connections. In this view, distance and separation are illusions. The cosmos is a deeply integrated whole, and what we perceive as empty space is actually woven together by an invisible fabric of instantaneous correlation. Entanglement doesn't whisper across the void. It simply demonstrates that there is no void to cross, hinting at a reality where the deepest connections are not geographical but informational, written into the foundational code of existence itself. But what if the very act of looking not only reveals reality but can actively prevent it from changing at all? This leads us to a bizarre and counterintuitive quantum phenomenon where observation becomes a form of control, a way to literally freeze a system in its current state through the sheer power of persistent scrutiny. This is the quantum Zeno effect, named after the ancient Greek philosopher Zeno of Elea, who proposed a series of paradoxes arguing that motion is an illusion, most famously that a flying arrow must actually be motionless at every individual instant of its flight. In the quantum world, this philosophical puzzle becomes a startling physical reality. The effect hinges on one of the most peculiar rules of quantum mechanics, the wave function collapse. As we've seen, when a quantum system is left unobserved, its wave function evolves smoothly and predictably, a process called unitary evolution. This evolution allows a system to change, such as an unstable particle decaying or an atom transitioning from an excited energy state to a lower one. However, the moment you measure it, you force a collapse. The system is pinned to a specific, definite state. Now, imagine performing this measurement not just once, but over and over again in rapid succession. Each measurement acts like a reset button, interrupting the natural evolution and forcing the system back to its starting point. If you measure it frequently enough, you essentially prevent it from ever having the time to evolve and change. You have quantum-watched pot that never boils. This isn't just a theoretical curiosity. It has been demonstrated in spectacular laboratory experiments. In one landmark study, scientists trapped a group of beryllium atoms in a superposed state, a delicate condition where they were both energized and not energized simultaneously. Left to their own devices, these atoms would naturally and quickly decay out of this state, but by repeatedly zapping them with precise laser pulses to check on their state, the researchers effectively froze the atoms in their initial superposition. The constant observation inhibited the very decay that would have otherwise occurred. It was a breathtaking demonstration that measurement is not a passive act of reading reality. It is an interactive process that can actively shape and constrain the behavior of quantum systems. The implications ripple out from the lab into the very philosophy of reality. The quantum Zeno effect suggests that continuous observation can literally alter the dynamics of the world, propping up unlikely states that would swiftly vanish without an audience. It adds a new layer of nuance to the role of the observer, painting them not just as a passive witness but as an active participant who can stabilize and preserve. Some have even speculated, though it remains highly controversial, that this effect could play a role in the stability of complex systems like our own consciousness, or that a universal form of observation might be responsible for the apparent solidity of the classical world around us. It presents a universe where existence is not a given but requires a certain amount of attention to be maintained, a cosmos where to be seen is in a very real sense to be. But what if the key to unlocking the true potential of the quantum world lies not in fighting its fragile nature, but in embracing a deeper, more robust kind of order? This brings us to a theory that is as mathematically beautiful as it is technologically promising, a concept that could finally tame the quantum realm for practical use. We're entering the domain of topological quantum computing, a vision for a machine that doesn't just calculate with quantum bits, but with the very fabric of space-time itself. To understand this revolutionary idea, we first need to confront the fundamental obstacle plaguing every quantum computer built so far: decoherence. As we've learned, quantum bits or qubits are exquisitely sensitive. A qubit might be a single atom, an electron, or a superconducting circuit, and its power comes from its ability to exist in a superposition of states. But this same property makes it incredibly vulnerable. A stray photon, a vibration, or even a passing cosmic ray can bump into it, causing it to lose its quantum information in a fraction of a second. This is like trying to build a tower of cards in a wind tunnel. The moment you create a delicate quantum state, the environment is constantly trying to knock it down. Engineers fight a never-ending battle to shield these qubits, cooling them to near absolute zero and isolating them from all external noise. But it's a losing war against the universe's constant churn. For quantum computing to ever realize its world-changing potential, from designing new medicines to cracking complex climate models, we need qubits that are inherently robust, not just delicately protected. This is where topology enters the stage, offering a profoundly different philosophy. In mathematics, topology is often called rubber sheet geometry. It's the study of properties that remain unchanged when an object is stretched, twisted, or bent but not torn. The classic example is a coffee mug and a donut. To a topologist, they are the same thing because one can be smoothly deformed into the other. They both have exactly one hole. The mug's handle is the donut's hole. The specific details, the mug's color, whether the donut is glazed, don't matter. What matters is the global, unchanging property, the number of holes. Topological quantum computing applies this same principle to information. Instead of storing data in a fragile physical particle, the idea is to encode it in a global, topological property of a quantum system, a property that is immune to local jostles and shakes. The magical particles that make this possible are called anyons. Unlike the two familiar families of particles, bosons and fermions, anyons exist only in two-dimensional systems and possess a truly bizarre property: they have a kind of memory. When two fermions or two bosons are swapped, their quantum wave function either stays the same or picks up a simple minus sign. But when you take two anyons and braid one around the other in a two-dimensional plane, their quantum state changes in a much more complex way. It's as if the path they take through space-time becomes part of their identity. The incredible robustness comes from this braiding. The information is no longer stored in the individual anyons themselves, but in the topological patterns of their world lines, the braids they form in space-time. A local perturbation, a tiny noise event, might jiggle an enyon, but it cannot change the overall braid pattern. It's like trying to change the number of holes in a donut by poking it with your finger. You might make a dent, but you haven't changed its fundamental topological identity. The information is protected by the laws of topology itself. Building a quantum computer with anyons would involve creating a two-dimensional electron gas in a semiconductor under a powerful magnetic field, a setup that produces the famed fractional quantum Hall effect, a state where anyons are known to exist. In this flatland, scientists would effectively create pairs of anyons and then physically move them around each other to perform braiding operations. Each distinct braid corresponds to a different quantum logic gate, the basic operation of a computer. The final readout of the computation wouldn't be measuring a fragile particle state, but simply checking the topological charge of the final braid configuration, a global property that is virtually impervious to local errors. This isn't just incremental improvement, it's a paradigm shift from error-prone correction to inherent error immunity. The implications of success are staggering. A fault-tolerant topological quantum computer could run algorithms for centuries without a single error, unlocking problems in materials science, cryptography, and fundamental physics that are forever beyond the reach of classical machines. But perhaps the most poetic twist is that the machine itself would become the ultimate laboratory. By manipulating anyons and observing their behavior, we wouldn't just be using quantum mechanics, we would be probing the deepest topological structures of reality, testing our most abstract theories about the universe in a perfectly controlled environment. It's a beautiful feedback loop. We use our understanding of quantum reality to build a technology that, in turn, reveals the quantum reality's truest, most robust nature. But perhaps the most profound challenge in our quest to unify physics lies not with exotic particles or hidden dimensions, but with a concept so fundamental to our existence that we rarely even question it: the nature of time itself. In our daily lives, time is the unwavering river that carries us from past to future. It is the stage upon which every event unfolds. Yet, when we try to weld Einstein's theory of gravity with quantum mechanics, this familiar river seems to vanish into a mist of contradiction. This is the problem of time in quantum gravity, and it suggests that our most intimate experience of reality, the relentless tick of the clock, might be the grandest illusion of all. The conflict arises from the two theories' completely different treatment of time. In Einstein's general relativity, time is dynamic and malleable. It's woven into the very fabric of space-time, a dimension that can be warped by gravity, stretched by motion, and even, theoretically, twisted into loops within a closed time-like curve. Time is relative. Your now is not necessarily the same as someone else's now. Crucially, the equations of general relativity are timeless in a specific sense. They describe the entire history of the universe as a single, frozen, four-dimensional block. There is no special present moment built into the math. The past, present, and future all coexist in this static sculpture. Now contrast this with quantum mechanics. In the standard quantum framework, time is not a dynamic player. It is an external, absolute background parameter. It's the unchanging metronome against which the wave function evolves. The famous Schrödinger equation needs this fixed concept of time to work. It tells you how a quantum system changes from one instant to the next. Time is the independent variable, the unwavering ruler we use to measure change. But this creates a glaring incompatibility. You cannot have a theory of quantum gravity where time is both an absolute background parameter and a dynamic relative dimension that gets warped by gravity. It's like trying to build a house on a foundation that is also one of the walls. The roles conflict. This has led some of the most promising approaches to quantum gravity to a radical conclusion. Time is not fundamental. Instead, it is an emergent property, a macroscopic illusion that arises from the collective behavior of more basic, timeless quantum entities. In this view, the universe at its most fundamental level is static. Nothing happens. Change is a derivative concept that only makes sense for large collections of particles. Much like the concept of temperature is meaningless for a single atom, but emerges from the statistics of trillions of them. Loop quantum gravity, for instance, describes space as a network of discrete loops. In this formalism, the equations that describe the evolution of this network strangely lack the time variable. They are known as the Wheeler-DeWitt equation, and they famously include the phrase time disappears from the equation. The theory doesn't describe how the universe changes in time. It describes how the different parts of the universe are correlated with each other. What we perceive as the flow of time might be nothing more than our journey through this vast web of correlations, a mental construction we build from observing one changing quantum relationship after another. This perspective turns our intuition inside out. Imagine the entire universe as a vast, timeless library. Each book in this library represents a single, complete configuration of the entire cosmos, a frozen snapshot. Now is one book, a moment later is another book, but the library itself exists all at once. Our conscious experience is like a flashlight beam scanning across the pages of these books in sequence. We have the overwhelming sensation of a story unfolding, of cause leading to effect, but the entire story is already written. The flow is not in the library, it is in the scanning. This is the block universe interpretation, and it receives startling support from the timeless equations of quantum gravity. It suggests that the past isn't gone and the future isn't unborn. They are just other parts of the grand, static structure that we are not currently looking at. If this is true, then what is the source of our unshakable experience of a flowing present? The answer may lie in thermodynamics and the concept of entropy. Entropy, a measure of disorder, is the only physical quantity that gives us a clear arrow of time. We remember the past and not the future because the past was a state of lower entropy. The famous arrow of time may be the real emergent phenomenon. Our brains are complex systems that constantly record memories and process information, processes that are thermodynamically irreversible and depend on the increase of entropy. In this sense, our very consciousness might be a machine that constructs the feeling of a moving now from the relentless increase of disorder in the universe. Time doesn't flow, we merely traverse a landscape where entropy consistently increases in one direction, and we mistake that directional gradient for a flowing river. This profound idea connects the physics of the cosmos to the biology of perception, suggesting that time as we know it is not a feature of the external world, but a story we tell ourselves to make sense of our journey through a timeless, correlated reality. Imagine the very stage of reality not as a smooth, pre-existing canvas, but as something that had to cool and crystallize into existence from a formless, chaotic fire. This is the radical proposition of quantum gravity, a theory whose name is a portmanteau of quantum gravity, and the idea that the universe is fundamentally a graph, a network of points and connections. It dares to suggest that space itself is not a primary ingredient of the cosmos, but a secondary, emergent property. In the beginning, there was no space as we know it. There was only an immense, seething network of innumerable nodes, each representing a fundamental unit of reality. In this primordial high-energy state, every single node was connected to every other node. This sounds like ultimate connectivity, but it's actually a state of featureless chaos. If everything is connected to everything else equally, then the concept of closeness or distance has no meaning. It's a universe of maximum information and minimum structure, a blindingly hot soup where geometry is impossible. The magic and the emergence of our familiar reality began as this network cooled. Just as water freezing into ice sees its molecules suddenly lock into a rigid, crystalline structure, the graph of the universe underwent a phase transition. Connections between nodes didn't just weaken, they were abruptly severed. In a process akin to cosmic annealing, the overly connected graph broke its links, leaving behind a new, sparser architecture. Most connections vanished, but a specific, orderly pattern of connections remained. This new pattern is what we now call space. The nodes that stayed directly linked became our notion of neighboring points. Distance is no longer an abstract concept. It is defined by the number of links you must traverse to get from one node to another. Two nodes that are directly connected are as close as 2 points can be. Two nodes that are 10 links apart are far away. In this breathtaking view, the three-dimensional continuum we move through is an average, large-scale illusion, a smooth picture that emerges from the microscopic, pixelated reality of a dynamic graph. This model provides a stunningly elegant potential answer to the ultimate speed limit in our universe, the speed of light. In quantum gravity, the speed of light isn't a fundamental constant stamped into the fabric of space-time. It is a consequence of the graph's connectivity. Information in this network can only hop from one node to a directly connected neighbor at a finite rate. The maximum speed at which any influence, any signal, any particle can travel across the entire graph is therefore determined by this basic hopping speed and the structure of the links. The cosmic speed limit is literally the speed of network traffic. This reframes one of Einstein's most famous postulates not as a law of space and time, but as a law about the underlying network that gives rise to them. Perhaps the most thrilling implication of quantum gravity is that it could make quantum entanglement feel less spooky. If two particles are entangled, their states are deeply correlated no matter the distance between them. In a standard spatial picture, this seems to require instant communication across a void. But in the gravity view, those two particles might be far apart in the emergent spatial picture, yet still share a residual, persistent link from the ancient, fully connected phase of the universe. They aren't whispering to each other across a vast emptiness. They are still holding onto a single, fragile thread from the original cosmic web. A direct connection that bypasses the conventional notion of distance altogether. Their entanglement isn't action at a distance, it's action via a forgotten shortcut, a relic of a time before space itself was born. This theory transforms our understanding of the vacuum of space. We think of nothingness as empty and inert, but in quantum gravity, what we call empty space is actually the ground state of this dynamic graph. Its most stable, low-energy configuration. The frantic quantum foam and virtual particles we associate with the vacuum could be understood as tiny, fleeting fluctuations in the graph itself. Brief moments where links attempt to reform or nodes vibrate, creating temporary ripples in the geometry of reality. This offers a profound new perspective on the universe's earliest moments. The Big Bang might not have been an explosion in space, but the phase transition of space. The moment the cosmic graph cooled and crystallized, freezing from a formless frenzy into a structured, geometric lattice, allowing for the concepts of here, there, and eventually us to finally exist. But perhaps no conflict in modern physics has been as deeply personal and intellectually fierce as the one that erupted between two giants of theoretical thought over the fate of reality itself. This was the Black Hole War, a decades-long battle of wits and principles between Stephen Hawking and Leonard Susskind. It began not with weapons, but with a single, devastating claim from Hawking in the 1970s. By applying quantum theory to the edge of a black hole, he calculated that these cosmic monsters must slowly evaporate, radiating away their mass until they vanish completely. The radiation they emitted, he argued, was purely thermal random, featureless heat. This meant that all the intricate information about every star, planet, or book that ever fell into the black hole, the specific quantum states that made them unique, would be irretrievably erased when the black hole finally disappeared. This information loss was a declaration of war on the most sacred rule of quantum mechanics, the principle of unitarity, which states that information can never be truly destroyed, only scrambled. Hawking was essentially saying that the universe has a fundamental forgetting mechanism, that the past could be permanently erased, rendering the cosmos ultimately unpredictable and unknowable. For Leonard Susskind and many other physicists, this was an untenable heresy. If Hawking was right, it meant the very foundation of quantum mechanics was flawed, and with it, all of physics. The battle lines were drawn. Hawking, the radical provocateur, was willing to sacrifice quantum mechanics' most cherished principle to follow his equations to their logical conclusion. Susskind, the staunch defender of quantum orthodoxy, believed there simply had to be a way out, a mechanism that would preserve information without violating other laws. The war was fought not in laboratories, but in the realm of profound thought experiments and complex mathematical duels. One of Susskind's key insights was the concept of black hole complementarity, which proposed a clever way to avoid a direct contradiction. It suggested that from the perspective of an observer falling into a black hole, information crosses the event horizon and is lost. But for an observer staying outside, the information never actually enters. It gets smeared and encoded onto the event horizon itself and is slowly radiated back out. Crucially, the laws of physics prevent any single observer from ever seeing both stories at once, thus preserving consistency. The war reached its climax not with a surrender but with a stunning reversal. In 2004, nearly 30 years after his initial provocation, Stephen Hawking traveled to a conference in Dublin and, in a move that shocked the physics community, publicly conceded. He presented a new calculation that showed how the intense gravitational fields around a black hole could indeed allow information to leak back out in subtle correlations within the Hawking radiation. The information was not lost, it was incredibly scrambled and hidden, but in principle recoverable. Hawking famously paid off his bet with Preskill, presenting him with an encyclopedia, a source of information from which information can be recovered with ease. Susskind and the preservationists had won, but the true victory prize was far greater than a settled bet. The long struggle to understand how information could escape a black hole led directly to one of the most revolutionary ideas in all of science, the holographic principle. If information isn't lost inside the black hole but is instead encoded on its two-dimensional boundary, the event horizon, then perhaps this is a general feature of reality. The principle boldly asserts that all the information needed to describe everything within a volume of space, every particle, every force, every dancing dust mote in a room, is actually encoded on the lower dimensional boundary that surrounds it. Think of it like a three-dimensional movie that is being projected from a two-dimensional screen. The image appears to have depth, but all the data required to create that illusion is stored on the flat surface. In the same way, our seemingly three-dimensional universe, with its rich tapestry of galaxies and life, might be a magnificent projection. The true, fundamental reality is a vast, two-dimensional information field that exists at the cosmic horizon, and we are living inside its immersive, holographic display. This transforms our understanding of reality at the most fundamental level. It suggests that the universe doesn't have three spatial dimensions in the most basic sense. The third dimension, along with gravity and the very fabric of space-time as we experience it, is an emergent property, a macroscopic illusion that arises from complex quantum interactions on a distant, flat surface. The holographic principle provides a powerful framework for finally reconciling gravity with quantum mechanics, as it allows us to describe gravitational phenomena in a volume using a quantum theory without gravity living on its boundary. It's a concept that is as humbling as it is empowering, suggesting that the solid ground beneath our feet and the vast expanse of the cosmos are, in truth, the most intricate and convincing illusion of all, a cosmic code written on the surface of the world, and we are the living, breathing output of that magnificent projection. But what happens when the quantum world, with all its delicate superpositions, meets the unruly and unpredictable nature of chaos? We've seen how decoherence explains the fading of quantum weirdness through environmental interaction. But in the realm of chaotic systems, this process isn't just accelerated, it's turbocharged. This is where the study of quantum chaos comes in, a field that explores how the principles of chaos theory leave their unmistakable fingerprints on the quantum scale, ultimately helping to slam the door on quantum behavior and usher in the familiar classical world we experience every day. To understand this, we first need to grasp classical chaos, the famous butterfly effect. In a chaotic system like the weather or a double pendulum, tiny, imperceptible differences in the starting conditions lead to wildly divergent outcomes over time. Two nearly identical states will evolve in such drastically different ways that predicting the system's long-term behavior becomes practically impossible. This extreme sensitivity is a hallmark of classical physics. Now, bring this same system into the quantum realm. A quantum version of a chaotic system, like a particle bouncing around in a stadium-shaped enclosure, would also like to exhibit this sensitive dependence. But there's a problem. The Schrödinger equation, which governs quantum evolution, is linear and deterministic. It doesn't allow for the kind of exponential sensitivity to initial conditions that defines classical chaos. This presented a deep puzzle for physicists. How does the chaotic behavior we see in the large-scale world emerge from a quantum substrate that seems to forbid it? The answer lies in decoherence acting as the essential bridge. While the quantum evolution of a single, isolated chaotic system is predictable, such perfect isolation is a fantasy. In reality, the system is constantly bombarded by its environment, and in a chaotic quantum system, this interaction has devastating consequences. Because the system is inherently unstable, with trajectories that want to diverge wildly, any tiny interaction with the environment, a single photon, a passing air molecule, gets massively amplified. This environmental probe doesn't just gently nudge the system, it kickstarts a chain reaction of disruption. The information about the system's state is copied into the environment, and then, due to the chaotic dynamics, that information is scrambled and spread out into the environment at an exponential rate. It's like trying to keep a secret in a small, quiet town versus a massive, bustling metropolis. In the chaotic metropolis, the secret doesn't just leak, it is instantly broadcast, distorted, and multiplied on every street corner until the original truth is completely lost in the noise. This explosive process of information lost to the environment is what causes decoherence to occur at a breathtaking pace. The quantum coherence, the ability of the system to maintain superpositions and interfere with itself, is destroyed almost instantaneously. The different possible states of the system can no longer see each other, and the system is forced to behave classically. This explains why we never see a chaotic system, like a tumbling die or a fluttering leaf, in a quantum superposition. Its inherent chaotic nature makes it exquisitely vulnerable to decoherence, causing any quantum behavior to vanish before it has a chance to be observed. The butterfly effect in the quantum world ensures that the mere flap of a butterfly's wing doesn't cause a hurricane weeks later, but instead causes the quantum description of that very wing to collapse into a definite state in a fraction of a nanosecond. This has profound implications for understanding the quantum to classical transition in the most complex system we know, life itself. living organisms are the epitome of complex, chaotic systems. Within a single cell, there are thousands of interconnected chemical reactions, proteins folding and unfolding, and electrical signals firing, a maelstrom of activity that is highly sensitive to initial conditions. The idea of a macroscopic biological object, like a cat or even a bacterium, being in a quantum superposition seems ludicrous, and quantum chaos tells us exactly why. The chaotic dynamics within a living organism act as a powerful decoherence engine. Any fragile quantum state that might form is immediately inundated and demolished by the chaotic storm of internal processes. The constant biochemical noise, the thermal vibrations, the flow of ions, all of it acts as an internal environment that continuously and ruthlessly measures the system, pinning it to a single classical reality. This doesn't mean quantum mechanics has no role in biology. Quite the opposite. Processes like photosynthesis in plants or enzyme catalysis are thought to potentially harness brief, protected quantum effects. But these are the exceptions that prove the rule. They occur in highly specialized, non-chaotic pockets within the cell, specific protein structures that are uniquely designed to shield quantum coherence from the surrounding chaotic frenzy for just long enough to be useful. For the vast majority of biological functions, the relentless churn of quantum chaos ensures that life operates firmly in the classical realm, its stability and predictability dependent on the very decoherence that prevents it from experiencing the bizarre reality of the quantum world. In the end, chaos is not the enemy of order. It is the architect of the classical reality we inhabit, the powerful force that sculpts the definite from the possible and gives us a world we can reliably navigate. Yet amid these grand theories of cosmic structure and information, perhaps the most intimate and profound mystery remains right here inside our own skulls. What is the nature of consciousness itself? That vivid inner experience of being that allows you to hear these words, to feel curiosity, to wonder about your own existence. For decades, the dominant view in neuroscience has been that the brain is a classical computer, a vastly complex but ultimately straightforward network of neurons firing in intricate patterns. But this view runs headlong into the infamous hard problem of consciousness. How does the purely physical electrochemical chatter of 100 billion brain cells give rise to the rich, qualitative, subjective world of sensations, thoughts, and feelings? How does the firing of a neuron create the experience of the color red or the taste of salt? This gap in our understanding has led a small but passionate group of scientists and theorists to propose a truly radical idea. Perhaps the brain is not a classical computer at all. Perhaps it is a quantum computer. This is the quantum brain hypothesis, a theory that suggests the secret of consciousness might be found in the spooky, subatomic world we've been exploring. The most famous version of this idea is the ORCH or theory, or orchestrated objective reduction, proposed by renowned physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. Their theory begins with a startling premise. Consciousness is not a gradual emergence from complexity, but a discrete quantum process. At the heart of their proposal are structures inside our neurons called microtubules. These are not just simple scaffolding, they are intricate lattice-like polymers that form the cytoskeleton of the cell, and Hameroff argues their structure is perfect for harnessing quantum effects. The theory proposes that within these microtubules, electrons can become delocalized, entering a state of quantum superposition. They wouldn't be in one place or another within the lattice, they'd be in many places at once, essentially performing a massive quantum computation. This superposition wouldn't last forever. According to Penrose's ideas about quantum gravity, this delicate state would be inherently unstable. After a brief period, the wave function would undergo an objective collapse, not because of any outside observation, but due to a fundamental instability in the fabric of spacetime itself. It is this moment of collapse, this quantum transition from a state of multiple possibilities to a single actuality, that Penrose and Hameroff propose is the basis of a conscious moment. Each collapse is a discrete event, and the orchestrated sequence of these collapses across the brain's microtubules is what gives rise to the smooth, unified stream of our awareness. The implications are staggering. It would mean that our conscious choices are not merely the deterministic output of neural circuitry, but involve a fundamentally non-algorithmic quantum gravitational process. It suggests a direct link between the physics of the very small and the phenomenon of consciousness, offering an explanation for qualities like understanding, intentionality, and non-computable intuition that a classical computer could never possess. Proponents point to the fact that anesthetics, which selectively turn off consciousness while leaving non-conscious brain activity intact, seem to work by erasing quantum coherence in these microtubules, while substances like psychedelics might enhance it. It's a theory that beautifully unites the objective world of physics with the subjective world of experience. However, the quantum brain hypothesis faces a mountain of fierce and credible criticism. The primary objection is brutally simple. The brain is simply too warm, too wet, and too noisy. Quantum states like superposition and entanglement are notoriously fragile. They require extreme isolation from their environment to maintain coherence, which is why we build quantum computers in massive, supercold, vacuum-sealed chambers shielded from all external vibration. The interior of a living brain is the absolute antithesis of such an environment. It is a bustling, warm, watery soup of jostling molecules, awash in thermal noise and biochemical chaos. Most physicists argue that any delicate quantum coherence in a microtubule would be destroyed by its environment in a time scale of femtosecond far too brief to play any meaningful role in neural processes that occur on the millisecond scale. To them, the idea is not just improbable, it is practically impossible, like trying to perform a delicate ballet in the middle of a hurricane. The debate between proponents and critics pushes the boundaries of both biology and physics. It forces us to ask whether there might be unknown biological mechanisms that could somehow protect quantum coherence. Could evolution have found a way to create sheltered pockets within cells, perhaps through orchestrated rhythms or specific molecular structures that shield quantum information from the relentless decoherence? Or is this a case of a beautiful, elegant theory being tragically slain by a stubborn, ugly fact? The quest to find evidence continues. Some researchers are designing experiments to detect subtle quantum vibrations in microtubules, while others are exploring the potential for quantum biology in other areas, like photosynthesis and bird navigation, to see if nature has indeed mastered these tricks elsewhere. Whether the quantum brain hypothesis ultimately proves right or wrong, its true value may lie in its audacity. It forces us to confront the deepest mysteries of our own existence with the most powerful tools we have, daring to suggest that the key to the mind might not be hidden in the chemistry of the synapse, but in the shimmering, uncertain, and profoundly weird heart of the quantum world. But even as we embrace the strange interconnectedness of quantum entanglement, we must return to the moment this profound weirdness was first thrust upon the world, a moment born not from acceptance but from a powerful and elegant rejection. This is the EPR paradox, a brilliant argument crafted by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935. Their goal was not to explore entanglement, but to prove that quantum mechanics, with its inherent fuzziness and probabilities, was an incomplete theory. Einstein, deeply uncomfortable with the idea that God would play dice, was convinced that a deeper, hidden reality must exist beneath the quantum quirks, a reality governed by strict determinism and locality, where objects have definite properties whether we look at them or not, and where no influence can travel faster than light. Their thought experiment was devastatingly simple. Imagine a single particle that decays into two identical particles that fly off in opposite directions. The law of conservation of momentum tells us that their momentum must be equal and opposite. Now, according to quantum mechanics, before any measurement, neither particle has a definite momentum. They exist in a blurred superposition of all possible momenta. But here's the rub. If you measure the momentum of the left-hand particle, you instantly know the exact momentum of the right-hand particle, no matter how far away it has traveled. From the perspective of quantum mechanics, your measurement on the left didn't just discover a pre-existing fact. It collapsed the wave function for both particles, instantly assigning a definite reality to the distant particle. To Einstein, this was pure magic, spooky action at a distance. He argued that this instantaneous influence was impossible. The only logical conclusion for EPR was that both particles must have had definite, predetermined momenta all along from the moment they were created. Quantum mechanics was merely a statistical tool that didn't have access to these hidden variables, this deeper layer of reality. They weren't saying quantum mechanics was wrong. They were saying it was incomplete, a surface-level description hiding a more sensible, classical underworld. For 3 decades, this argument stood as a powerful philosophical challenge, an unprovable but deeply persuasive critique. It took the genius of an Irish physicist named John Bell to find a way to drag this philosophical debate into the concrete world of experimental physics. In the 1960s, Bell devised a breathtakingly clever mathematical proof, now known as Bell's theorem. He showed that if Einstein was correct, if there were local hidden variables determining particle properties before measurement, then the results of certain correlated measurements would have to obey a specific mathematical limit, now called a Bell inequality. However, if quantum mechanics was correct in its spooky entirety, then these same measurements would violate this inequality. Bell had found a way to test the very nature of reality itself. He provided a recipe for an experiment that could, once and for all, determine whether particles carry secret instructions from birth or whether they truly forge their reality through instantaneous communication. The experiments began, most famously by Alain Aspect and his team in France in the early 1980s. They were careful, precise, and designed to close every conceivable loophole. They created pairs of entangled photons and measured their properties in different directions simultaneously, ensuring no signal could travel between the detectors fast enough to cheat. The results were unequivocal and earth-shattering. The experiments violated Bell's inequality. They spectacularly confirmed the predictions of standard quantum mechanics. Einstein was wrong. There are no local hidden variables. The particles did not have predetermined properties. The reality of one particle is indeed instantly influenced by a measurement made on its distant partner. This wasn't a flaw in our knowledge. It was a feature of the universe. The interconnectedness, the non-locality, the spooky action, it was all real. Bell's theorem and the experiments it inspired forced upon us a revolutionary and inescapable conclusion. We must abandon one of 2 deeply held intuitions about the world. Either locality, the idea that distant objects cannot instantly influence each other, or realism, the idea that objects have definite properties independent of measurement. We cannot keep both. The universe has chosen. Most physicists have chosen to abandon locality to save realism, leading to the many worlds or other interpretations. But the core lesson remains the same. The universe is fundamentally probabilistic and profoundly interconnected in a way that defies our classical mechanical worldview. It is not a collection of separate, independent things, but a vast, entangled web where the properties of one part are intimately tied to the whole. The EPR paradox began as an argument for a quieter, more reasonable cosmos, but it ultimately led us to the thunderous, beautiful, and undeniable truth of our quantum reality. Yet for all the breathtaking success of quantum field theory in describing the particles and forces we see, it contains a ticking time bomb, a single number so wildly wrong that it threatens to unravel our entire understanding of the cosmos. This is the vacuum catastrophe, and it represents the most staggering failure of prediction in the entire history of science. To understand it, we must return to that seething quantum foam, the vacuum of space that is alive with virtual particles constantly popping in and out of existence. Every cubic centimeter of empty space, according to quantum field theory, is a raging ocean of this vacuum energy. The theory allows us, in principle, to calculate the energy density of this vacuum. We can add up the contributions from every known quantum field and every possible fluctuation. The result of this calculation is a number so mind-bogglingly enormous it defies comprehension. The predicted vacuum energy density should be around 120 orders of magnitude larger than the energy density of the entire observable universe. That's a 1 followed by 120 zeros. This number is so catastrophically large that if it were true, the repulsive force of this vacuum energy would have instantly blown the universe apart in the first fraction of a second after the Big Bang. Galaxies, stars, planets, and life would have been utterly impossible. The universe would be a featureless, accelerating void, empty of any structure whatsoever. But when we look out at the universe with our most powerful telescopes, we measure something completely different. In the late 1990s, astronomers made a shocking discovery. The expansion of the universe is not slowing down due to gravity, as everyone expected, but is actually accelerating. Something is pushing the galaxies apart. This something was dubbed dark energy, and its measured energy density is incredibly small, but not zero. It is a positive, tiny number that fits the observations perfectly. However, when we compare this observed value to the one predicted by quantum field theory, we find ourselves facing a problem of epic proportions. The observed vacuum energy is a staggering 120 orders of magnitude smaller than the prediction. This isn't just a small error, it's like predicting a tidal wave the size of a galaxy and instead observing a single, solitary drop of water. It is the worst mismatch between theory and observation in all of physics. This discrepancy is so profound that it cannot be brushed aside as a simple miscalculation. It points to a fundamental flaw in our understanding, a deep crack in the foundation of modern physics. There are only a few possible explanations, and each one is radical. The first possibility is that we are somehow calculating the vacuum energy incorrectly. Perhaps there is a hidden symmetry or a cancellation mechanism we haven't discovered that makes all these enormous positive and negative contributions from the quantum fields cancel out almost perfectly, leaving behind only the tiny residue we observe as dark energy. The problem is, no one has found any evidence for such a perfect cancellation. It would require a level of fine-tuning so exquisite, so precise that it seems almost miraculous. This leads to the second, even more mind-bending possibility, the anthropic principle. In a vast multiverse where different regions or bubbles have different physical constants and different values for the vacuum energy, most universes would have a huge cosmological constant and would be blown apart instantly. Only in the incredibly rare bubbles where the vacuum energy is almost exactly zero, by a random chance of 1 in 10 to the 120th power, could galaxies form and life emerge. We find ourselves in such a universe not because it's special, but because we couldn't exist anywhere else. This is a deeply controversial idea because it suggests that some of the most fundamental properties of our cosmos are not dictated by a unique law, but are merely environmental accidents. A third possibility is the most unsettling of all, that we are fundamentally wrong about how gravity works on the largest scales or how it couples to the quantum vacuum. Einstein's theory of general relativity has passed every test thrown at it with flying colors, but it has never been tested in the regime where the gravitational effect of the quantum vacuum becomes important. It's possible that a theory of quantum gravity, like string theory or loop quantum gravity, will provide a completely new way to understand the energy of empty space, one that naturally yields a value of zero or very close to it. The vacuum catastrophe, therefore, is not just a puzzle about a number. It is a blazing signal that we are missing a crucial piece of the cosmic puzzle, a piece that must somehow unite the quantum world with the force of gravity in a way we have not yet imagined. It is a silent, haunting reminder that the void itself holds the deepest secrets of the universe, and that our journey to understand it has only just begun. But perhaps the most compelling reason to take the concept of a multiverse seriously is its power to answer one of the most profound and enduring questions in all of science and philosophy. Why is our universe so perfectly tuned for life? This is the puzzle of fine-tuning, and it suggests that the fundamental constants of nature, the numbers that define the strength of gravity, the mass of an electron, the force that holds atoms together, appear to be exquisitely, almost miraculously, calibrated to allow for the existence of stars, planets, and conscious beings like us. If any of these values were even slightly different, the universe as we know it would be impossible. A little stronger nuclear force, and all the hydrogen in the early universe would have fused into helium, leaving no fuel for stars. A little weaker, and no elements heavier than hydrogen would ever form. The force of gravity is perfectly balanced to allow for the slow burn of stars over billions of years rather than a rapid collapse or a dissipating void. This delicate balance of so many independent variables feels less like a happy accident and more like the universe won a cosmic lottery with odds so astronomically against it that it begs for an explanation. The multiverse provides a stunningly elegant, if humbling, solution to this riddle. In an infinite or near-infinite ensemble of universes, each with its own random set of physical constants, perhaps generated by the eternal inflation of space-time or the pinning of different landscape values in string theory, every possible combination of laws will eventually be realized. The vast, overwhelming majority of these universes would be stillborn or barren. They might flash into existence and collapse immediately into black holes, or they might be so diffuse that matter never clumps into galaxies. They could have forces so weak that atoms never form, or so strong that everything is locked into iron. In this cosmic landscape, universes that are hostile to life aren't just likely, they are the norm. But in a multiverse of incomprehensible size, even the most improbable outcome becomes inevitable. Somewhere, by pure chance, a universe will have just the right combination of constants to allow for complexity and life to emerge. We find ourselves in such a universe not because it was designed for us, but because we are a product of its rare, life-permitting conditions. We could not exist anywhere else. This application of the anthropic principle transforms fine-tuning from a mysterious hint of design into a straightforward selection effect. We should not be surprised to observe a universe fine-tuned for life. We are precisely the kind of observers who can only exist in such a place. This perspective doesn't diminish the specialness of our existence, it reframes it. We are not the predetermined pinnacle of a cosmic plan, but we are incredibly fortunate winners in a cosmic game of chance. Our universe is one tiny, shining bubble of order in a frothing sea of chaotic or sterile realities. The quantum processes that spawn these bubbles, from the fluctuations of inflattened fields to the decoherence of wave functions, become the very mechanism of cosmic exploration, generating every possible reality in a relentless creative process. The multiverse, therefore, is not just a theory about other worlds, it is a necessary framework for understanding our own. It suggests that the quantum weirdness we observe in the lab, the superposition, the branching, the uncertainty, is not a quirk of small things, but a glimpse of the deeper, generative engine of all reality. The same quantum principles that allow an electron to be in two places at once, on a cosmic scale, allow for the existence of every possible universe, including this one, perfectly tuned for us to be here, wondering at it all. And so our journey through the looking glass reaches its end for now. We've ventured from the splitting branches of the many worlds interpretation to the participatory magic of the Copenhagen view. We've seen reality argued as a simulation, a hologram, and a cosmic code waiting to be deciphered. We've grappled with black holes that might erase information or encode it on their surfaces, and we've considered the possibility that our own consciousness could be a quantum process dancing inside the neurons of our brains. Each of these 30 theories, in its own extraordinary way, pulls at a different thread of the tapestry we call reality, challenging the very core of what we think we know about existence. What unites them all is a single, powerful message. The universe is far stranger, more vast, and more mysterious than our everyday senses could ever suggest. The solid ground beneath our feet, the predictable sunrise, the unbroken arrow of time, these are comforting illusions. A simplified user interface our brains have constructed to navigate an underlying reality of pure potentiality and profound interconnection. These ideas are not just abstract intellectual exercises. They are invitations to expand our minds, to cultivate a sense of radical wonder, and to embrace the beautiful, humbling truth that we are only just beginning to understand our place in the cosmos. The greatest takeaway from this exploration is that the question is far more important than the answer. The pursuit itself, the act of questioning, of experimenting, of daring to imagine the impossible, is what pushes humanity forward. It's what transforms us from passive inhabitants of a mysterious world into active participants in a grand cosmic story. Whether you find yourself drawn to the infinite possibilities of the multiverse, the elegant geometry of string theory, or the intimate consciousness of panpsychism, remember that each perspective offers a unique lens through which to view the magnificent puzzle of existence. Now we turn the conversation over to you. This is just the beginning of a much larger discussion. Which of these theories resonates most deeply with your own view of reality? Did the cold logic of quantum Darwinism win you over, or were you captivated by the timeless beauty of the transactional interpretation? Share your favorite theory in the comments below. We are genuinely excited to hear which ideas sparked your curiosity and challenged your perceptions. If this journey through quantum realities expanded your mind, make sure to subscribe and hit the notification bell, because we have so many more mysteries of the cosmos left to explore together. Thank you for joining us on this incredible adventure. Keep questioning, keep wondering, and never stop looking up and inward at the wonder of